you've made it hopefully to the right room. This is the Cartopy tutorial. And the tutorial is entitled Around the World in 80 Ways. And that's a play on the excellent book written by Jules Verne, Around the World in 80 Days. And your hosts today are myself, Phileas Fogg, and my useful assistant, humble servant, Bill Passepartout-Little. We're both software engineers at the UK Met Office, the National Weather Service for the UK. We work in the analysis, visualization, and data team. And for our day job, we do kind of lots of Cartopy and data type stuff. So this is right up our street. Yep. So I've already highlighted the repository with the content. It's in github.com/scitles/cartopy-tutorial. And I've just spotted, honestly, we weren't pushing things like 4 hours ago or anything. So if you have been organized and actually cloned this repository before today, you're going to need to pull and get the latest updates. So that's basically just a git pull on that repository, and it should bring in changes on master. Yeah, maybe 1 o'clock in the morning, or maybe 5 o'clock in the morning. We're not sure. Yeah. It's a bit of a blur. So, if you're having any issues, there is a Slack channel, SciPy 2018. It's hashtag Cartopy, I think. Neither Bill nor myself have access to that Slack channel while we're presenting, but we've got a couple of helpers around the room who'll happily do that. In fact, I'm going to point them out. In this corner, we've got Juan Nunes Iglesias. I've asked Philippe over here to look out, and I can already see there's a couple of other ringers in the room, like Joris in the background. If any of you want to just help out, kind of contribute if there's any questions on the Slack channel, that'd be really useful. Thank you. Great. So there's a question from one of our Slack helpers asking how to use Slack. So, I would say, ask on Slack, but a bit of a problem.
I am now on the Slack. Yeah.
Okay, so let's get going without further ado. So this tutorial really is about giving you some background on Cartopy, predominantly. But we're not going to shy away from using kind of geospatial terms. I'm going to talk you through some of those concepts. And I guess Cartopy doesn't sit on its own in an island. It is part of a bigger ecosystem. And we want to give you an experience of using those tools kind of, as I say, Cartopy and friends in a kind of cooperative way. So that's basically what we're trying to get out of this. Yeah. So as I say, the repository's there, github.com/scitles/cartopy-tutorial. And for those that have just walked in, if you've been organized and pre-cloned this, please pull, because we've made some recent changes. There'll be a couple of handouts coming around for some of the exercises that we do. There's a requirements.txt to kind of get all the dependencies installed. Can I get a quick show of hands who's already got a working Conda environment? Okay, that's pretty good. So it's super useful if you've already done that, because it takes quite a while to kind of download everything and install it. If you haven't, there are some instructions on the README of this repository. And if you get stuck, throw it on Slack, and hopefully someone can help you out. Yeah, so that's the channel. Hashtag Cartopy on SciPy2018.slack.com. If all goes terrible and you're not able to install on your machine, there is also a MyBinder link on the repository. I'll click on that, in fact. As I say, wasn't recent or anything. If you don't have an environment working and it's taking too long or it fails for any reason, there is a binder option that you can kind of just click on this and get an interactive version of the notebooks online too. Okay. So this is pretty much the outline of what we're going to try and do today. We're going to start with some kind of basics about what projections are, and not shy away, as I say, from using geospatial type words. We're then going to, actually that whole section is pretty much not going to touch Cartopy at all. It's going to be kind of an interactive learning experience that hopefully will set us up for the next section, which is about Cartopy and the Matplotlib interface. And then we'll start looking at, this is where really Cartopy and friends come in. We'll then start looking at how you interact with some of these tools that are part of the wider ecosystem to do quite powerful things. I guess before we go too much further, we should say that neither Bill nor myself are particularly experts at geospatial stuff. And in fact, writing this tutorial has been quite an eye-opener, even though we were able to kind of write Cartopy. So take that to heart. Don't feel like this is some complex thing. We can hopefully get through it, and yeah, we'll all be able to use kind of consistent words and understand what things like projections really are. Okay. That is that. So that's some background. I'm going to stop for a second, stop speaking. Is everything going okay in terms of installations and getting the materials? Do we need to? Okay, so this really focuses on map projections more than anything else, if I'm honest. We'll use some of the geospatial terms whilst going through that, but it'll just give you a sense of what projections there are and why there are different projections, I guess. So again, purpose for this really is to help you understand the terms used in Cartopy documentation and the wider geospatial literature. And just as importantly, given that there are lots of map projections out there, to help you get a sense of when a projection might be appropriate for your particular application. Okay, so I guess we should start with this statement. The world is not flat, despite what some people seem to insist. And there's lots of ways we can prove it. Well, I was quite surprised when I looked up flat Earth, and they gave me this picture here, which is an azimuthal equidistant projection. And this is the ice wall of Antarctica is what holds us in on this flat Earth, apparently. Yeah. What can you say? We'll get into some of the details of what this projection actually looks like in a bit, but the reason we have to have map projections is because the Earth is not flat. Unfortunately, most of our media is flat. So paper, screens, they're all pretty two-dimensional. There are exceptions, like a 3D rendering engine, or you can buy these globes that have got projectors in them, that kind of stuff, but they're pretty niche. So we need projections. And a map projection is a systematic transformation of the latitudes and longitudes of locations from the surface of a sphere or an ellipsoid onto the locations on a plane. Great. But there's a problem with map projections, all map projections. And that is that in order to go from the sphere onto a plane, you have to cut somewhere. There is no way of not cutting. And not only that, no matter what you do, you're going to distort some properties of the underlying representation. So the kinds of distortions we're talking about there, area, shape, direction, distance, scale, these are kind of fundamental things that we want to be able to represent in our visualizations. And yet, all projections mess some of these things up. Okay? So the reason you have to understand what a map projection, or when to use a particular map projection, is so that you can preserve the things that are important to you. I'll give you some examples of when you might want particular preservation properties in a minute. So Phileas Elson, the host of this tutorial, has coined a quote, which I think is going to be massive. And that quote is, all map projections are wrong, but some are useful. By wrong, this means they're going to break some of your metrics. So you have to understand that. So as I say, there are lots of map projections out there, and there are a couple of approaches to classifying them so that you can actually talk about these things. And they are essentially by how you form your map projection, or you classify based on what metrics they preserve. Let's start with surface classification. So there are three main types of surface classification that map from the sphere onto a plane. You can use cylindrical type projections, which the name kind of gives it away. You construct a cylinder and you map the lats and longs up onto your cylinder. There's azimuthal, which is a plane that you put on top of your sphere and project out. Or there's the conic form, which I'm not even going to try and describe. The thing is, this is a really nice kind of simple way of separating your types of projections, but there's only a small number of projections out there that actually fit nicely into these categories. After that, you start having things like pseudo-cylindrical, pseudo-azimuthal, or you have all sorts of random things like things that are basically bolted together that are none of the above. So this approach is only kind of so good. But cylindricals, as I say, this is basically a cylinder mapping to the lats and the longs. And one of the defining features of a cylindrical projection is that meridians and parallels are straight and perpendicular. Okay, so as you can see on the map there, your meridians and your parallels are perpendicular and straight. Okay, and this image is really nice because it gives you some of the other words. I'm not even going to use them, but yeah, you can rotate the cylinder. It doesn't have to be aligned with the poles, and you end up with kind of an oblique. Or if you go entirely rotate 90 degrees, you get a transverse. Azimuthal projections. Again, there's some words there. So you've got the polar azimuthal projections. You've got equatorial, which are planes touching the equator, and then oblique azimuthals are where they're touching somewhere that's not the pole or the equator. And some of the interesting properties of azimuthal projections is that the parallels are complete circles. Okay, and what's kind of interesting about azimuthal too is that there's normally one or two central points on an azimuthal projection, and from those central points, all great circles are straight lines. Okay. Just to be clear what a great circle is the shortest, it's the path of shortest distance on the sphere. Okay. I have a handout in a minute with lots of these words written down, so if I'm using too many words too quickly, then hopefully that will help. And finally, the conic projection, again, not going to talk too much about it, but what's interesting about conic projections, or what's kind of iconic about conic projections? Sorry. Meridians are straight lines, so they're not parallel, but they are straight. Okay? And the parallels are circular arcs, and they're not fully circular. They're just the arcs. So that's kind of a very obvious feature of conic projections. And it kind of normally results in you having that curve at the very top of the projection, and at the very bottom, obviously. So at that, I'm going to hand over to my handsome assistant, Bill Passepartout-Little, who's going to talk about projections by preserving metric. And, yeah.
Okay, so good to see you. So we're going to mix things up just to keep a bit of different cadence, so you don't like fall asleep in your seat. Conscious of that, but we know that you're probably getting a bit twitchy. You're not like writing code just now, but we're leading up to a kind of interesting exercise, a paper exercise. We're going to force you to get up and chat and meet people, but that's a good thing, right? All this this nomenclature, that's a difficult word for me to say with some jet lag, is that we try to build up a common language that we can use later on. So everything's common, we know what we're talking about. First time using the Mac, I just found out it scrolls the opposite way. It freaked me out. Okay, so if things are a bit clunky, I'm just going to press buttons, so you can just laugh at me. Okay, so we're going to talk about some of the things that Phil was saying that gets distorted when you've got your sphere and you project it onto a plane. You're going to lose some behaviour, whether it's distance, shape, scale, all these types of things. And there's names for if you want to, you know your data, and you have to think about rather than making a cool kind of map projection that looks nice and show people, but you want to actually represent your data in some way, and you want to focus on it in a certain way. So you want to preserve some of those behaviours. So with conformal, it's all about conserving shape. You might care about that, the outlines of boundaries of countries, or anything that you care about. And there's some examples there of Mercator, transverse Mercator, that actually preserve that shape anywhere on the projection because you care about it. But it might be at the compromise of other metrics or other, like distance or area, things like that. So there's a compromise to be had, but you need to be sort of wise to what projection you need and when to use it. Keep on using the cursor keys, spacebar. Right, so zooming in, zooming out. So when you zoomed in for large-scale maps, it's you're preserving shape. So you want to preserve the shape of that. The major drawback is that their lengths and areas can be distorted, and there's you put that in. There's a famous example where Google kind of shot themselves in the foot somewhat, where they used a projection that just didn't work. So they addressed that. So they choose a projection that wasn't suitable for all areas. So you have to be careful in what you want to choose, and it's got to be representative for everybody that wants to use that projection. Zoomed out, so this could be something like Mercator, and it's used for like nautical charts where you're keeping a run line, your distance and bearing. It preserves that. So you have to think about how you want to use that, how your shape works. Equidistance, so as it says, it's preserving the distance. So if you care about measuring distance between points on your projection, then you might pick equidistant, but it might be at the compromise, as I said, of something else. So the projection is preserving distance between standard points or lines. And there's examples that we'll come across. And there's an example later on where we're going to look at some projections, and you have to guess which is what's preserved, what's lost. Okay, so equal area. So talked about shape, talked about distance, and you might actually care about area for whatever reason. So there are projections that preserve this, but and there are a lot of them. But again, you have to pick the ones that you want and hopefully minimize the distortion of the other kind of metrics that are there. So it suits your needs. You have to pick and choose, really. And of course, nothing, as Phileas said, it doesn't fit neatly into buckets like that. Life's just not like that. So there are compromises that you can make, and there are projections out there that they might not cover all the bases, but they're good enough to show your data in a way that you care about the most. And you just have to find them and pick them. So a lot of words, and it's nice. I'm quite visual. I like to see what we're talking about, and we have the Tezos indicatrix, which is it's a way in which you can see for a projection what's happening, what's going on, how is it being distorted in terms of distance, shape, and area, and basically you're drawing on projection onto your chosen projection circles that are there that can get distorted depending on the projection. So here we see that we've got, does this work? Yes, it does. So with this kind of example, you're seeing that you've got nice circles here, but as you're going up in near the poles and latitudes, there's some squishing and stretching of the circle. So that tells us a lot of information. And how does that help us? So going back to the three things: conformal, equal area, and equidistance. So given that, circles in the sphere will remain as circles because they're being preserved for the shape. So that's a hint that that projection can be conformal. Okay, pretty obvious. Equal area. So circles of constant area in the sphere will be, so they could be distorted, but you could sort of guess that they might cover the same sort of area by looking. So they might be stretched, lose their shape, distance might be lost, but the area is roughly the same. You can kind of judge it by eye. And another sort of heuristic that you might want to use is that when you look at Greenland, it should be in a ratio 1:14 with Africa. So if you see it really stretched, then you know it's not equal area. So these are little hints that you're going to have to use later on. We're coming up to an equidistant. So the distance, these are preserved along the meridians. So in your projection, you'll see, particularly if you look at the meridians and the parallels, the distances will be the same. They're not going to be stretched. Okay, so that's another little hint there. Okay, so this is the fun part. This might actually blow up in our faces, or it might actually be fantastically good. So Phil is going to go around. He's handing out some handouts, obviously. Basically, this is going to have to be a collaborative effort. You're going to have to get up and chat to your neighbours, because basically you've got the sheet, and on the sheet there is a table, and on the table you'll see there's a projection name. We talked about things being conformal, preserving shape, if it's equal area, if it's equidistant, and the type of classification that it was. Now there are eight actual projections labelled A to H. Okay, you've probably either got 3 or maybe 4 of them. You've not got all of them. Okay, so what you've got to do is you've got to fill out this table. So you've probably got 3 images, but your neighbour might have a different 3, and then the other neighbour's got another different 3. Okay, so what you've got to do is you've got to figure out, fill out the box in terms of, is it conformal? Okay, is it equal area? Is it equal distance? Okay, and once you've got that, then you can work out for each plot A, B, C, D, E, F, G, H. If it matches up with this, you should be able to write in, complete the table and say projection A is Mercator or whatever. Okay, is that clear? Yeah. Any questions? So you're going to have to chat. How long are we going to have on this?
Okay, so in the interest of kind of giving you all the same information, how about we talk through this number A, and then we can build up from there. How does that sound? Does anyone want to talk us through any of the particular properties of this projection? So I guess we want to find out first about whether it's conformal, Then we'll talk about equal area, equidistant, and its type. So, is this projection conformal, and why? Okay. Okay, so someone said no because the circles aren't the same size. Okay. Yeah, and has corrected yourself because they're not circles, right? So conformal is about whether these are circles or not. So on the sphere, these are circles. But when projected onto this map, they're clearly not. We've got an awful lot of stretching going on, if I can find a mouse, down here. Okay, so quite clearly, this projection is not conformal. Okay? Everyone happy with that conclusion? Equal area. This is slightly harder, and because humans are kind of notoriously bad at determining area, so this is why we got this exercise wrong when we were kind of doing it ourselves. But this one, hopefully, is kind of visible. Are these circles on the sphere represented in an equal area on this map projection? Okay, no. And again, the obvious ones are, we've got this circle here and this great big thing over here. Okay, so definitely this projection is not equal area. Okay, equidistant. Okay, and I'm going to put a condition on equidistant. Equidistant along the meridians. And I've already had a yes, so talk us through it. Why is it equidistant along the meridians? What visual clues have you got there? Okay, so the distance between the latitudes is the same along the meridian. So you're basically looking at the gap between these parallels, and it looks roughly the same all the way along this meridian. Okay, and another meridian, the distance is roughly the same all the way along. Okay, so that's a good indicator. Are there any other visual indicators that we could be looking at? Right angles, that's interesting, but I think that's a property of conformal more than of equidistant. So it's a similar trick. You can look at the height of the projected circles, okay, along the meridian. The height of this circle might not look it, but is the same as this height, which is the same as this height, which is the same as this height. If you had a ruler, you could verify that. So I agree, this projection is equidistant along the meridians. So let's try and classify the developable surface, the type of projection that this is. Any guesses? So I've heard cylindrical. That sounds sensible. What evidence do you have for that?
So we looked at it basically on a sort of a plane, some kind of plane of projected a certain longitude and end up with a projecting. That's the shape when you end up with when you project.
Okay. The good word there is rectangle, definitely. And right, meridians and parallels are straight, cross at right angles. This is, without a doubt, a cylindrical projection. Okay. And hopefully, if I bring up that tab, if I can actually escape from here, maybe I can. Hopefully, if we cross-reference this table, we should be able to see that we said no to conformal, no to equal area, yes to equidistant, and that it's a cylindrical. Okay, and the no, yes, cylindrical turns out to be an equidistant Plat Carré projection. Okay, so you've got now 1/8 of the exercise complete. I might talk you through one other projection before we go too much further. No, I won't. I'll let you go too much further, and then sorry. I am cruel. If there are any questions, just put your hand up and we'll keep coming around. But keep going on this exercise. There's still quite a lot to be got out of this. Okay, so there was a natural lull in volume there. And I think that's a signal that probably we've kind of done this one enough. So let's talk through what you found. Hopefully you'll have made the same mistakes that we made, because we're all human, we make mistakes, and we'll learn from that. That's kind of the idea. Okay. So we've looked at A. So I just wanted to say thank you as well for engaging in that exercise. It was great fun to see everyone kind of talking and not using computers. I know this is a tech conference and everything, but this is about people as much as anything, this conference. So B. Does anyone want to talk us through some of the properties of B? There's a sweet for anyone who does. Candy, sorry. Okay, so the suggestion is it's conformal. Excellent. I would say it's not equal area given, as you say, that circle and that circle don't really look that equal area. Good, great. There's a good hint. Excellent, well spotted. Greenland and Africa are definitely not the same size, but they look it on this map. Okay? Okay, and not equidistant because this length and this length are definitely not the same. Great, okay. And what type of projection do you think this is? Okay, and what clues do you have to say that it's cylindrical? Okay, yeah. Yeah, so Mercator projection, and that's a very good guess, I would say, not guess. Well induced. So where are we? Conformal, not equal area, not equidistant, cylindrical. It's a Mercator. Great. And true to my word, Candy. I can't run up all the stairs for everyone, so you'll have to come down and get it if you want some candy. So next plot, if I can not get lost. Right. So slightly different. Anyone want to talk us through some of the metrics? You don't have to talk us through all of them if you don't want to. So it's conformal because circles are circles on this map. Yeah, great. Yeah, so not equal area, that circle's definitely smaller than that one.
And you can see also it's not equidistant because distances as you go outside it's getting bigger and bigger.
Okay, not equidistant because these lengths are getting bigger and bigger. That way.
I think it's going to be...
Okay, what evidence do you have to say that it's conic?
I think it's like, for me, I think it's the shape. Like, all of the projection.
Yeah. It's not full circle or rectangle. That's a good way of kind of getting there. The other clue is that the parallels are arcs. Not complete circles, but they're arcs. And you get that kind of very obvious arcy baseline here. Right? It's very arcy. So great. So you said equal area, but nothing else, and it's conic. So what projection did you determine that to be? Okay, so, sorry. Yes? I didn't catch what you said, I think.
So we found it basically on the list of projections in the on equidistant corner.
Okay.
It's the same one, but I think it's not equidistant, it's just the name.
Right.
But it's 100% wrong.
But you said it wasn't equidistant,
Yeah.
so it's definitely not equidistant conic.
It's Wikipedia, guys.
Okay.
That's why.
So, okay, let's talk through the list then. So you said it was conformal because the circles were circles. You said it wasn't equal area because we were getting bigger circles. You said it wasn't equidistant. So we're looking for a tick here and crosses elsewhere and a conic. Well, the first one here is the conformal, not equal area, not equal distant, and it's a conic. I think that's a good way. It's the Lambert conformal projection. Great, thank you. Please come and treat yourself to some of the finest candy that AT&T Conference Center can offer. Okay, again, very different projection. Anyone want to help us through this one? The circles aren't circles, okay, so it's not conformal. Okay? Okay, so they're getting thinner, so it could very well be equal area. And as we said before, humans are terrible at guessing whether it's equal area or not. So. Okay, yep. So this is definitely longer than that length there, so not equidistant. Pseudo-cylindrical parallels are parallel, but meridians become curved. Yep. Okay, good. So not conformal, equal area, not equidistant, pseudo-cylindrical, sinusoidal projection. Great. More candy. Okay. E. Any volunteers? Okay. Yeah, so definitely not conformal. That circle is not a circle. Yeah. Sorry. Okay, doesn't look to be equal area. I think, yeah, that's fair. Yeah. So along the meridians, you're saying equidistant. So this came up a few times in conversations. So we're following a single meridian, and along that single meridian, we're looking for the distances to be the same. Okay? So the size of that distance there is definitely not the same as that distance there, if you can see my cursor or not. But along this meridian, they're all about the same. So equidistant's a good shout, I'd say. Yeah, azimuthal because we've got complete circles for the meridians. Yep. The naming, the more obscure we get, the easier the naming gets, right? So azimuthal equidistant is the name of the projection. It's also an azimuthal equidistant projection, which is great. Did anyone spot that red line? Okay, so this red line, we didn't really talk you through it, is a great circle from latitude 0, longitude 0 to New York. Okay, and in every other projection we've seen so far, there's been a slight curve to that red line. Okay, slightly curved here, definitely curved there, curved here. Okay, but that's this azimuthal projection that we've just seen is the first one where it's actually been pretty straight. Okay, and this azimuthal projection is centered at 0, 0, and all great circles out of 0, 0 on this map projection are actually straight lines, which is a really nice property in some situations. Okay, F. Any?
I think F is going to be informal.
Yeah, so
Optimal circle.
the circles are definitely circles, and yeah, conformal,
Yeah, not equal area.
not equal area.
And, I think they're equidistant. You go to one to two.
The suggestion is that it's equidistant, but I'm going to zoom in a little bit and try and take another look at that.
Oh, okay.
So, yeah, I think that circle there, if you use the little hand cursor, it kind of, yeah, definitely that circle there is significantly taller than that circle there, and it's on the same meridian. So I think it's not equidistant. Okay. And the classification of that projection? As a moved projection, yeah, again, that same property that we saw last time, that red line is a straight line, the great circle's straight. And as you say, we've got the complete circles. Complete. Yeah. So
The distances on that great circle from 0, 0.
the distance of the great circle is not preserved.
0, 0.
The direction of the great circle is preserved.
Direction and distance from 0, 0. So at the center of the Earth, if you're at that location,
Yeah,
and you want to know how far is it to New York City,
yeah,
or how far is it to Antarctica,
yeah.
you can measure it.
Okay. You sound very confident, so I'm going to take you on your word for that, because it always blows my mind. Okay, that's good fact.
So to the floor of the airport, down,
Right,
how far are we from?
right. Okay, it's good knowledge.
I mean, we said no to conformal, no to equal area, we said also no to equidistant.
You said yes to conformal,
Oh, yeah.
because the circles were still circles.
Okay.
So the name of the projection, stereographic, yeah. Okay, let's try and get through these last few. So G. Okay, so you worked backwards on this one. So you knew the name of the projection then? Yeah. Right. Yeah, so you know it's a Robinson. Yeah, so it's not conformal, and you can definitely see that that's not a circle. Okay, so you said about equidistant there. Did anyone get that wrong? Because I did when I did this one, because that looks quite equidistant to me. Does everyone else get this right? Yeah. They kind of looked like it to me. So the one near the pole here is... Okay. Okay. Yeah, that's fair. I didn't have a good eye for that. I'll get this wrong. So.
I got that wrong as well.
Yeah. But no one else did. So that's excellent. We should come to these guys.
They should teach us.
Yeah, yeah. And you were about to tell us the classification of the surface. Okay. Yeah, that's fair. Did anyone get more specific than other in the end? Pseudo-cylindrical. So what properties did you pick out that suggest that this is pseudo-cylindrical? Okay, so parallels are actually parallel, and the meridians are curved. Yeah. Okay. Great. He did the same for figuring out that this is a Robinson. And then he was like, okay, so what properties is a Robinson?
Yeah.
Sorry? Of course you can. Come and get candies. Yeah.
You take two.
Right, last one. Someone who's not already been offered candy. Anyone? Oh, yeah. You should come and get candy. I'm putting your hand up as well. Yes, please. Okay. Yeah, clearly not conformal. Yeah, roughly equal area. So you're stating the equidistant along the meridians. So let's just take a look at that. Would everyone agree with that? Yeah, so my little hand cursor thing here is roughly the height there, and then it's nowhere near the height there. So I'm pretty sure that's not equidistant. And you can also see that the distance between here and the distance between here are definitely not the same. So yeah, not equidistant. Okay. Conic, because we've got lines and arcs, yeah. Yeah, so a conic projection that's equal area, the Albert equal area conic projection is right. Excellent. That's that exercise. As I say, thank you for engaging and kind of making that a fun exercise and communicating. That was really enjoyable and could have been less enjoyable, definitely. So I'm going to, hand back to you, I think. Is that all right?
Can you get to the tab, Phil? Did you get to the tab at the top?
Yeah.
There you go. Okay. Okay, so that was fun. Phil says, like he said, thanks very much for engaging in there. So we've now kind of got a basis to sort of go forward, understand a little bit about the language of projections, and there's different features there, different metrics. So what we're going to do now is we'd like to sort of start dipping into Cartopy, because that's basically why we're here. So and the interface of Cartopy with Matplotlib specifically. So the good thing about Cartopy is that it integrates really well with Matplotlib. So if you use Matplotlib, hopefully you do, that it's not a bolt on top of it or a wrapper around it. So there should be no sort of surprises when you're using Cartopy and Matplotlib. So we're going to look at some of the documentation that we've got there for Cartopy, because we matured over the time. There's lots of gallery examples and tutorials and information that we've been talking about. It's worthwhile knowing that it's there. They've got a projection list. You can go and have a look at things like that. And also get familiar with how Cartopy and Matplotlib play together, really. Okay. Let's go there. Oh, it's the opposite way. Got me every time. I'll get used to it by the end. So the documentation, we host it at SciTools. Like I said, there's a ton of stuff there. It's worthwhile going. We're not going to, we'll dip into bits here and there. As I say, there's a little introduction, there's a definitions list, there's some installation guides, but we're on Conda if you've been using that. We talk a little bit about Matplotlib, how it's structured, the class hierarchy, some of the key words that we use for Matplotlib to integrate within Matplotlib using the transform and the projection keys, and we'll touch on that later on. And there's sort of rich features that are in there, shape readers, we'll touch on that later on, and how you can get involved. So you can take the time and have a look at that. We'll dip into some of the bits later on. But Cartopy itself, it's what we try to do is that there are a lot of projects we're really engaged with open source, and there are a lot of projects out there that do things really, really well. And Cartopy has joined the dots on some of those things that stands on the shoulders of giants somewhat, because we're building on top of Proj 4. So if you're using projections, reproject and things like that, you're going to use Proj 4. NumPy, of course, and Shapely for which is on top of Geos to control your geometries. And of course, if what you get with Matplotlib, you get your publication quality maps, you kind of get that for free with Cartopy. It just works. So it's additive to it. So it might have some specializations in extra behavior, but it plugs in quite nicely, and we'll point that out as we go along. And it's object oriented. We'll point that out later on. But basically, what it comes down to, we understand projections a little bit more now. So what we care about in this world is then, well, we want to represent our data on our projections. So what we're thinking about here are 5 things, which is points, lines, vectors, which are like your special case of lines with direction and magnitude, polygons, and then raster images. And Cartopy can handle all of these. It's got some smarts under the hood that kind of makes your life easier, particularly when dealing with some interesting projections. We have a so we're talking about projections. So there's a class that represents projections, and we sort of specialize that. We've got subclasses of that represent each of the projections. Each of them have got a certain different behavior, and we've tried to kind of make it easier to interface, sort of humanize, or make it rather than using bubble Proj 4 parameters up. We've tried to make it easy to sort of use with the keyword arguments, so it's sort of obvious what we do. And sometimes you have to take a stance on defaults. So we try to make sensible defaults, but you can change them, obviously. But we're going to start with something simple like plat carry. So we looked at that before. I guess you guys you can either watch or you can sort of run along as I'm going through the notebook. But if you've got your everything set up, so if we're going to talk about projections, what we tend to do is everything lives in the CRS package. So, and we just call it CCRS. So we're going to import that. And there's a whole bunch of projections. We just jump into the documentation. These are the kind of things that we saw in that exercise. We've got information about each one, keyword arguments that come in. So plat carry, we've got you can change the central longitude in the globe that's there, the upside datum that's underneath. There's lots there. You've got each of the representation, and then you can see how you can control that projection, what keyword arguments you can pass in to control it and manipulate it in the way that you want to visualize your data. So that's all there. We're not going to go through them all, but it's worthwhile knowing that we keep going back to that again and again as developers. So it's a useful kind of resource to have. So okay, so we've imported CCRS, and now we're going to instantiate a class. So it's simply we're just going to create a projection, and sure enough, Cartopy has come back. It's created a projection. We've got one. So what can we do with that? We're in the world of projections, so we want to see what we've got. So let's this is where we integrate with Matplotlib. Matplotlib, needless to say, just as an aside, you don't need to use Matplotlib with Cartopy. You can just use it for projecting your data. And if you want to visualize it, you can use Matplotlib. But it sort of stands on its own in that regard. And I think we've got some exercises later on that sort of show that, because you might not want to actually plot your data. You just want to change the numbers and reproject it. So we're talking about Matplotlib. The currency there is axes, but an axis, it doesn't understand any geospatial information. So this is the kind of cool thing about Cartopy, is that it understands the language of Matplotlib, and it gives you back an axis-like thing, but it's got the smarts in it that understand how you want to plot on it for maps. And it's a geo-axis. So you can look in the documentation, but there's more information about that. And there's methods. Let's go there, why not? Quick. There we go. So we've got a class of geo-axis, and there's a whole bunch. I keep scrolling wrong. We've added extra methods in there, which some of them we'll dip into, you'll see throughout the tutorial, and there's other ones you can go off and kind of explore in your own time, adding raster images, all sorts. So these are kind of inherited for each axis, and you can use them because they're there. So we'll find out about those later a little bit later on. Right. So okay, we've talked enough. Let's see a projection. Okay, so we're going to use the Matplotlib notebook, import Matplotlib. So the key thing here, really, and this is what's kind of nice, the way that it interacts with Matplotlib, is that there's nothing new here. You can create a normal axis in Matplotlib as you would normally do like this, but we've used the projection keyword, which was already existing, and you pass in your Cartopy projection. So this is telling you this is what the projection that you want to see when you do the plot. So we're saying make an axis, and the target projection is plat carry. So on that, and there we are. That's the tutorial finished. Thanks very much for coming. I hope you've enjoyed yourself very much. There's not a lot there. It's just an axis. You can't actually see anything, but what we'll do. Oh, how do I get out of this, Phil? Can I go back? No, it's not scrolling. Oh, that is right. I was in Mac panic mode there. Okay, so we've done our plot. It happens. So there's nothing really there. It's just an axis, nothing different. But it is actually a geo-axis that we've got back. And you can do plots, and you can do subplots as well. So it just works. But if we want to see something, it would make life a little bit better. So there we go. So there's some stock things that I said, some of the methods that are on the axis that are kind of useful. So here again, we create an axis, a bog standard thing in Matplotlib. You're saying, what I want to see is a plat carry projection that you all know and love by now. And we're saying, well, actually, now I've got the axis, just draw some coastlines. And we sort of lean heavily on natural earth. We provide some low resolution coastlines, and you can change the resolution. So here we are, we've got our plot, looks like a plat carry, got some coastlines, fantastic. So it's that easy. So you can change that projection to anything that you want that's in our projection list. Okay. And of course, it said there should be no surprises. That's what we've tried to aim for with this integration of Cartopy and Matplotlib. So it should just work for subplots. Same deal. I'm going to use Matplotlib vanilla subplot. We just created our pass in our projection again, subplot keyword argument, add in our coastlines again. We've got a subplot. Hurrah! So it's all good. No surprises. So that's what we've been kind of aiming for. So for you guys, hopefully that you've got an environment that's running. We've got a little exercise for you. So we've got time for this. How long have we got? Maybe a couple of minutes? No? We'll see. Give it a try. Okay, so what I want you to do is to go to the documentation. There's a link there. You'll see information about the plat carry projection. Use that information to help you to create a global plat carry map with coastlines. But the difference is, we've just done that, but the difference is I want you to center it on the dateline, which is 180 degrees longitude, rather than Greenwich Prime meridian. Okay, so use this cell in here to write your answer. If you clicked on that, you'll get the answer. So you can click on it and have a look if you want. But just try. It's not a million miles away from the example that we're using here, but you have to do something different to tell the projection where the central longitude is. Do you want to give that a try? Or is enough people got their environment up and running? Hands up if you've got your environment up and running. Right, do you want to give it a crack? See, 5 minutes? Got time for that? Yep.
Okay, let's not labour this one too much. So hopefully you managed to get to the documentation. So Cartopy docs. Let's go there. There is a projection list document, which Bill pointed out. And the Platte carrier projection is the first one, because it's kind of a pretty common map projection. And there's this keyword on the map, on the Platte carrier class, central longitude, and it's that we want to change. Okay. I'm completely lost now. There we are. So we've already imported Cartopy CRS as CCRS, which is kind of a common pattern. I'm just going to put it into a variable, ccrs.platte-carré, and that central longitude there, we can just set it. Okay. Before I go too much further, it was suggested that I point out that you can look at the documentation for this class in the notebook directly if you want to. So you can just put a question mark after the object that you want documentation on, and Jupyter will pop up a little bit of information, and yeah, you can also see there central longitude can be set. Okay. So that simply can be set like that. Plot.axes projection. So this is that dance that Bill showed us. The projection keyword argument. When you're making an axis, you just pass it a projection object. I'm going to capture that, and finally, I'm going to make use of that super useful method, coastlines. Okay, and if you actually do a plot.show, and don't. Right, so one of the issues is we're using the notebook backend, and you need to remember to make a figure each time you want to make a new figure. Kind of sensible, but easy to forget to do it. And the result, if you're not as zoomed in as me, is a map centered on the antimeridian, approximately the dateline, in Platte carré. And I have the same issue of scrolling out of there. Good. Any questions on that? Have I done what the solution told me to do? Yeah, so it captured a Platte carré object, 180, and used it in exactly the same way. Okay. Any questions? Observations? Right. No, but the key is that the axes that you're getting back here is a Cartopy geo-axis. It's not a Matplotlib axis. So this function here, this plot.axes, is basically a Matplotlib factory function. It constructs an axis for you, and it's the keyword arguments that you pass which determine what type of axes you get back, which is going on there, basically. So the result is a Cartopy geo-axis, and I'm going to actually just talk about the useful methods of that geo-axis in a bit, so we'll actually get a bit more experience of what you can do with one of these things beyond just calling the coastlines method. Any other questions? Okay, so let's do that. Let's find out more about that geo-axis object. I guess maybe before I do, I should just do a type on that axis, just to really prove to you that this isn't a Matplotlib axis. This is a Cartopy Matplotlib geo-axis. Okay, this is the thing that Cartopy defines, and that's documented in the Cartopy documentation. Maybe make that a little bit bigger. It's a geo-axis, and it's a subclass of an axis, so you get all of that behavior, plus a bunch of other behavior on top of that. Okay. I'm going to start tidying up a little bit, because too much stuff. That's a really good suggestion, yes. So that instance we can also get some docs on using the same trick, the question mark at the end, and it kind of gives us some information there about what's available. Yeah, I learned about that the other day. That's a good trick. If you really want to see how this has been implemented, you can do a double question mark, and it kind of gives you this source. Never done it before, didn't work. Maybe that's in. We found a bug, maybe. Scrap what I just said. One question mark will give you the help on that object. Okay, so we've already seen one of those methods on the geo-axes, which definitely doesn't live in the Matplotlib axes, and that's the coastlines method. Right? It doesn't make sense for there to be a generic coastlines on an axis in Matplotlib, but it completely makes sense for a Cartopy geo-axes. In addition to that, there's a couple of other really useful geographic type methods. The grid lines method allows you to kind of draw graticules, so parallels and meridians. And there's also a really low resolution natural Earth image that you can just throw onto the axes using stock_image, and that'll give you basically a bit of blue and a bit of green, just so that it doesn't look quite so white. Yeah, so the question is how low is that, and it's really low. So at a global scale, it'll look fine. Not great, but fine. But at any kind of zoom, you're going to want a different image. Okay. And the main reason for that is that we ship some very basic coastlines, and we ship this very basic image with the package, and we don't want the package to get too big. So there are a bunch of other interfaces, which I'm not actually going to show you, to get higher resolution coastlines and higher resolution images as well. I guess on that front, you would normally add an image to a Matplotlib axes using the imshow method or the imshow pyplot function, right? The same's true with Cartopy. You can just use that imshow method. But with Cartopy, we've added some extra behavior, which we will look at shortly. But there are a couple of other new methods that don't exist. So there's add geometries. And for those familiar with Shapely, basically you can directly add a Shapely geometry onto the axes, and it will project it for you. And then finally, a little note about these two. So set global basically will zoom out the map as much as the projection allows. So global is kind of a questionable word, but that's what it's trying to do. It's just zooming out as much as possible. And set extent allows you to kind of set a bounding box for how zoomed in you want, or the extents of your map that you want. So again, all of these except imshow are new to the geo-axes, and even imshow we've kind of overridden in the geo-axes. Question?
With the add geometries, does that also have GeoPandas functionality, navigable data frame, or just the geometry function?
So there's a question about GeoPandas, and it would be remiss of me to answer that when we have Joris sitting in the room, who's the resident GeoPandas expert. So Joris. Okay, fine. That,
There is an example in the gallery of the different representations of the physical but as far as I know, the activity there needs to be explicitly but you can always get them out of
okay, thank you. Great. So let's take a look at some of those things. So there's a little example here. We make another plat carré projection because it's so easy to see things in plat carré, and that axes object that we make, we use the set extent method, and we pass a bounding box through. Okay, and I always get them mixed up. It really upsets me that I always get them mixed up. This is xmin, xmax, ymin, ymax, I hope, now that I've said this publicly. But yeah. On top of that, we're also using this new grid lines method, which you can basically pass Matplotlib type keyword arguments through. And so these are fairly standard kind of interfaces for Matplotlib. You can change the alpha, you can set the line style, that kind of stuff. And there's also a magic draw labels keyword on here, which will kind of basically give you the words. And we're also going to see that lowish resolution background image. Okay, let's run that, and then I can show you a picture. And let's do something about that figure size. I'm going to zoom out just a little. That'll be fine. Right, so I was right, after all. So it's from minus 170 longitude to minus 50 longitude. Yeah, minus 10 to plus 80 latitude, good. And you see the labels have been drawn. We've got a grid line going over the top, and we've got a fairly, well, you can see how poor the resolution is there, Juan. You know, it's not a particularly high resolution, but it gives you a nice splash of blue and green, I think is probably all you can expect from stock image. Okay. Right. So there are a bunch of kind of tools on top of what Cartopy, tools that Cartopy provide, I guess, and better ways of getting more data. But let's kind of start fairly manually. So Natural Earth is basically a collection of really amazing data sets that they have. And I have pre-downloaded an image in the resources folder, which is a slightly higher resolution image, as it happens. And there's nothing stopping us using standard Matplotlib stuff to load in an image, or you could use stuff like scikit-image, pillow, anything basically that's going to give you a NumPy array to represent this image. And it's 1000 by 2000 by 3 color channels. And in addition to that, I'm all over the place here, excuse me, I'm also going to load in a states shapefile. Okay, so this is a shapefile which contains the outlines of the, I think it's just US states. Okay, and we can use Fiona for this. GeoPandas would work just as well if you're familiar with that, or you can do the really manual approach and use PyShape. In this case, I've just used Fiona. So basically, I now have an array up here which represents an image, and I have a list of shapely geometries. Okay, these are pretty fundamental geospatial data types that have got nothing to do with Cartopy really. And you just add them to a Cartopy geoaxis by using fairly standard methods. So imshow will do the trick. You add an image, that's the array. This is a Matplotlibism to tell you that the pixels start at the top rather than starting at the bottom. Again, with Matplotlib, you can control the location of where this image should be plotted, so we do precisely that. But there's this really big, important thing that you have to also know about when it comes to Cartopy, and it's this keyword here, the transform keyword. Okay, and this is basically, this is kind of one of the major points with Cartopy is you can specify the map projection that you want and the transform of the data that you're adding when you add it. Okay, and we'll see this time and time again. This will keep coming back. I'll point it out again, I'm sure. But we're specifying the transform of the image. And then this geometries method, add geometries method, basically we pass that list of geometries, the coordinate reference system that those geometries are in, and very standard Matplotlib keyword arguments when you're making any type of patch or, yeah, Matplotlib patch, I guess. Okay, I'll stop talking. Let's look at picture. So we have now definitely, I can see it, I hope you can see it from back there, a higher resolution image here, which is much more pleasant. And I've overlaid US states on top of that image. Okay. So all of this is basically additive on top of Matplotlib's standard axes methods. We're just adding geospatial aware data on top of that. Yours. So the question is, these geometries, is it assuming they're in lat-salons? And the answer to the question is definitely not. So you're telling it that the geometries are in lat-salons by providing that coordinate system. Okay, and they could be in anything else that you can represent in a Cartopy coordinate reference system. Okay. No. So the question is, are we specifying here the target coordinate system? And the answer is completely not. This is the coordinate system of these geometries. Okay. And if you want to change the target coordinate system, you do it in your map projection when you're setting up your axes. Okay. So the map that you're producing is defined in the axes. The axes knows what map it's making. And when you're adding data, you're telling it what coordinate system your data is, not what it should go to. Okay. Thank you. That's a very useful thing to get clarified. We'll talk about this again more, but does that make sense? Is everyone comfortable with what's going on there? Okay. So the question basically is, if I have a satellite image, what map projection is that in? And there may be satellite experts in the room, and I'm sure they will all wish you good luck, if I'm honest, because it's really hard to find out what projections things are in. Often, you will be able to get satellite products that are projected for you, and that's always a healthy place to go from. There is a good example in the gallery, and that segues nicely. Let's do that. So the Cartopy documentation has a gallery. It could always have more pictures, definitely, but there is an example of that. And I'm going to actually, I think I'm going to be brave and show you the code here, because as I recall, we've got an image, but the image projection is actually a geostationary object. It's not plat carré. These aren't lats and lons. These are crazy extents. They're not lats and lons in extents either. And we end up just simply using imshow, and you're setting that the transform is geostationary. It's not plat carré. Okay. And yet the map that we're looking at is a plat carré. Okay. So a bit more scrolling, sorry. No, there we are. Got myself in a puddle. It's not plat carré, it's a Miller projection. But the key is the projection of the image is not the same as the projection of the map. Okay. Great. So then, there. Right, so the question is, the three examples I've put forward now have made three separate instances of plat carré. Does it make sense to consolidate that in some way? Is that representative of your question? Actually, there is a bit of a cost to creating a plat carré object. It's not particularly high, but if you were in a for loop and you're making thousands of these things, then yeah, you would definitely be considering bringing that out, putting it into a variable and reusing it. The only reason I've not done that here is it just makes things much more readable to see exactly what's going on. And it also means I can do crazy things, I think. And this is never a good idea, but I'm going to do it anyway. Hello? Oh, no, okay. That was a terrible idea. Let's not go there. Oh yeah. Oh, Mercator. Right, okay. Right. This is interesting, right? So that image that I added, if you remember, was plat carré. The data I added was plat carré, but the map we're looking at is definitely not plat carré. Right? So something's happened here, and the reason that took a little while is that the image had to be reprojected. So Cartopy is not the fastest. It's quite general in its kind of ability to reproject images, but it does it eventually. And so that's what's actually happened here. But it's also reprojected a bunch of other things like the states outlines, okay? Because they were in plat carré, but now they're clearly not. So. Good. Don't go off-piste is the right. Right. So some interesting notes from here. So we're doing more work than we need to. So Cartopy already knows how to draw states, and it's actually quite simple. You just add the states feature, and it'll just do the right thing. One of the really nice things, as Bill was pointing out earlier, is that we're building on top of Matplotlib. We're not kind of re-implementing our own interface. So if you want to change the color of the face that Matplotlib is drawing, you use the Matplotlib keyword argument face color. And if you know Matplotlib, then you know what keywords you need for Cartopy. Okay. Which is nice and consistent and all that kind of stuff. And yeah, this key thing, which I'm going to keep laboring throughout this section, I think, is the transform keyword argument that we used is what specifies the coordinate system of the data that you're adding. So when we added geometries, we're specifying the coordinate system of the geometries, not of the map that we're making. Okay. It's when we use that projection keyword argument to make the axes, that's when we're saying what projection this map should be in. And they're two independent things. Right. Again, keep laboring this. So why it's important to specify the coordinate system of the data as well as the projection of the map. So these things are independent, and I guess one of the really most important things that I'd like you to take out of this really is that Cartopy is designed to reproject your data for you. On the whole, Cartopy will do the right thing when it comes to poles, antimeridians, interpolation, and map boundaries. Okay, which, if you've ever tried to kind of project a line that crosses the dateline or something like that, you realize that it's very easy to get it wrong and mess up. Cartopy tries to do a better job. Okay, so it's a nice feature. Okay, so I guess a little bit more about that transform keyword argument is in order. Sorry, question. Great.
So you just said that you showed an example of changing the underlying projection and keeping the transform image the same. If you just change the image, though, like what is it? How do you know what? I mean, someone said before, how do you know what projection your image is? Like if you change the image.
Okay, so the question really is, why would any image not be just plat carré? Why is there any other projection out there? I guess, or how is it encoded in some way? So plat carré is the simplest of simple projections because 1 degree of longitude is the same as 1 degree of latitude. Okay, and in an image, that's a really kind of convenient property, and you'll find an awful lot of images are handed out like that. Fundamentally, I guess fundamentally they're laid out differently in an image for different projections, and it's just different properties. I'm not sure that's a great answer, but hopefully that. Right. So let's dig a little deeper on this transform side of things. And let's start drawing a line between 2 points. Okay. Now, on the sphere, there are several ways of drawing a line between 2 points. And in a projected space, there are several ways of drawing a line between 2 points. Let's pick two of the most common. So between 2 points on the sphere, you probably, or often, I guess, will pick the shortest distance on the sphere, which, as you saw with that red line in the projection exercise we did earlier, doesn't always result in a straight line in a map projection. Okay? On the other hand, sometimes you might actually want a straight line in the map projection, perhaps because the map projection has a particular property, and you want to preserve that in your line. Okay. So there's a little example here. We've got picked out some coordinates of two cities, where we've got the longs and the lats, picking them out, and we're just using Matplotlib here, axes.plot. I should say that could equally be plt.plot. It doesn't really matter, just prefer to use the axes object method, pass the x's and the y's, and again pointing out lons and lats, not lats and lons. You'll find that ubiquitously in Cartopy that pretty much lons come before lats, x's and y's. So standard plot with the transform keyword argument, and I'm saying plat carré, these are lats and lons. Okay, the default plat carré instance represents lats and lons nicely. And yeah, I guess I've added a label, and we'll see what that looks like in a second. Let's plot this and go from there. Let's look it through a bit more. Right, so we've got something to talk about now at least. So we've got two lines between 2 points, and they're not the same line. Okay, one is clearly a straight line between the 2 points in this projection, and the other is clearly not a straight line in this projection. Okay, but it turns out that this not straight line thing is the shortest line on the sphere. Okay, it's a great circle, whereas this thing is not. Okay, so let's talk a bit more about that. So the line that the equirectangular straight line is plat carré. Plat carré is a projected coordinate system. It's Cartesian, and a line between 2 points in a Cartesian coordinate system makes an awful lot of sense to draw a straight line in that coordinate system. Okay, which is why we're seeing a straight line in plat carré. On the other hand, there's this other object in Cartopy, the geodetic coordinate reference system. It's not a projection, you can't make a map of it, but it tells Cartopy that when you're drawing a line between 2 points, it wants them to be a straight line on the shortest straight line on the sphere, a great circle. So this geodetic thing is quite magic in that it's kind of telling Cartopy how to draw the line. It just so happens both geodetic and plat carré understand lats and lons. It's just how the line is interpreted which is different. The only other thing that's worth noting here, I guess, is you know that work we did earlier to add the states using add geometries? You can actually just import Cartopy feature states and add it to the axes, and it'll just work. Okay, so useful. Any questions on that? Okay. Yeah, okay. So you're pointing out that the great circle is pretty ugly. It's not particularly smooth, okay? Which is great, and I'm going to move on to that right now. So let's fix that in a second. Any other questions for that? Juan's desperate to know because he gave a tutorial the other day. Right. Actually, I'm not going to go straight onto that. I'm going to go onto that in a second after this section, if that's all right. Remind me of the question if it's not answered. Let's do something slightly different with this map. Okay. let's pick a projection where the great circle is a straight line. Okay, and that naturally will mean that this straight line here, we'll replot it, won't be a straight line in the projected space. Okay, bit mind warpy, but can anyone put forward a suggestion for a projection that would preserve the direction of a great circle, keep a great circle straight from a particular point? Mercator's a suggestion. That's interesting. It's not quite right, but I can see why someone might have said that. Who was it that said it? Right, a stereographic would do the trick. What kind of projection is stereographic? What's the developable surface of a stereographic projection? Yeah, azimuthal, someone said, yeah, right. And all azimuthal projections have this property where from the central point, the great circle is a straight line. Okay, so we could pick any azimuthal projection. Stereographic is a great example. We do precisely that, in fact. So let's construct one of these stereographics. And I'm actually going to pull up the documentation because it's worth going there. So that projection list is the second one down in the getting started. And eventually, if you can see down the list, there is a stereographic. And there's a bunch of keyword arguments you can change, including the central latitude and the central longitude. Okay. And all I'm going to do is set up a map projection which has the central longitude at one of the points that I care about. I think I've picked New York. Okay. And that means that any great circle out of that point is going to be a straight line. So we should see some interesting properties coming out of this. So set up a stereographic centered on New York. Set the extent in lats and longs, add some grid lines, add the stock image, add the states, and draw the great circle and the straight line in plat carré space. Okay, let's take a look. Okay, taking some time because it's reprojecting that image into stereographic, but it came out again, and this time that great circle, as we hoped, is a straight line, okay? But that equirectangular straight line that we drew before, which used to be a straight line, isn't a straight line in this coordinate system, okay? If we cross-reference it, though, we'll find that it actually goes through the same points as it did before. I'm not going to jump around too much, but if you're following this on your own machines, then you could see that kind of like definitely goes through here, and it definitely goes through here. Okay, so this is just the same data being presented in a different projection. Okay, and I guess this is the key point about Cartopy is you tell it what projection you want, and you tell it when you're adding data what coordinate system that data's in, and the rest Cartopy will deal with. Yeah. So core principle Cartopy gives you map projection portability and Cartopy enough context to project your data for you. That's the key take-home message from this section, really. But in answer to your question, the big downside of automatic reprojection is, in reality, you don't have an awful lot of control. It's not easily controlled, and there is a performance cost, and we were seeing that when we were reprojecting that image. Okay. So, for example, the lines in the previous spots are noticeably low resolution. So this is demonstrating that Cartopy, whilst it looks like it's producing curves, it's actually making straight line segments. It's just having to kind of approximate and interpolate to an appropriate resolution. And it turns out, actually, that resolution is probably not appropriate for the plot that we've produced. So right now, there's a little bit of a workaround to improve that. There's this threshold property on a projection object. And basically, I'm subclassing the stereographic projection, and I am giving that threshold, I'm just making it, getting the threshold lower. And I guess this is interesting because it shows us that we can also create map projection, Cartopy projection objects ourselves. We don't actually need this to kind of be built into Cartopy. This is something that you can actually extend yourself if you need to. So I make a higher resolution stereo. I'm doing exactly the same things I was doing before, not changing any of the code. That function which draws the line is exactly the same. And the result is working. A much smoother curve on that line. Okay. So to be clear, just to continue answering that question fully, we've increased the tolerance, the threshold, on the target projection, not on the source projection. Okay. So when we're converting our lines, there's an iterative process that's going on, and it figures out, for this map that I'm making, how many times do I need to refine this line so that it looks nice and smooth. And that's precisely what we're controlling with that threshold keyword. Okay. Right, that's the geo-axes and some of its methods. So we saw imshow, we saw add geometries, we saw that useful coastlines method, we saw what else have we seen? Set extent and set global. And basically we can throw data onto a map in pretty much the same ways that we can with Matplotlib, plus a couple of useful ones for common geospatial type stuff, including shapely geometries. Okay. So I'm going to rest my voice a little bit and let Bill talk about the main theme of this tutorial, and that is around the world in 80 days. Okay.
Okay, so around the world in 80 days or 80 ways. That was our spin out. So Phil's kind of set us up quite nicely. So we have been building up in layers about understanding projections, what they are. There's different types, and how in Cartopy that neatly blends into Matplotlib. There should be no surprises there. The way we control the source projection and the target projection, just use the transform and the projection keyword. So we're going to pull this back to our whole kind of abstract, which was around the world in 80 days. So anybody read the book? Long time ago. Seen the cartoon or something like that, yeah. So Jules Verne. So we have Mr. Fogg here, who is he's taken a wager and he's going to go around the world, and it's quite nice. It's just a means to for us to kind of sort of showcase Cartopy, because we want to show his route that he took in his 80 days around the world, different projections, how we can control that, how that works. So we're going to sort of tug on that theme a little bit and explore different parts of it. So for you guys who have got an environment, we're going to do a little exercise here. So Phileas Fogg, this handsome chap here, on the run with his carpet bag and £20,000 to go around the world, plans to travel around the world in 80 days. So he set off in October, and then he got back in December. He plans to depart from London, and his main stops, the main routes that he took, he went to Suez, Bombay, Calcutta, Hong Kong, Yokohama, San Francisco. I think our spelling of San Francisco is a bit flaky some places, but we're British, so hey. New York City, and then back to London. Okay, so knowing what we know, we want to be able to draw a map to show this route. Okay, so we've set you up with, here are the places, and here are the longs and lats. So we give you, what time do you know? Just as long as it takes, yeah. So drawing on what Phil had sort of shown you to do a plot, can you draw, I think we've got it in Placari, perhaps, yeah, that's the one we've shown. Can you show the route of Phileas Fogg when he went around the world? So this is going to help you so you know the places and you know the longs and lats. So we'll give you a bit of time to think about it. Essentially, you're going to use creating the right projection for Placari, and then you're going to plot these points and draw the line. Okay. So we just realised that with the break, we thought the break was at 30:30, but snacks are served until 30:30. So we've got that slightly wrong. So what I'll do is I'll quickly zip through this answer and then break, and you guys can have a comfort break, which is good. So not to get too hung up on this, it's simply we're thinking about drawing a line on a map. So you've used plot basically with Matplotlib. The difference is that we are kind of forcing out the space of thinking about projections. So you know that you want to have, use Cartopy, you've got geo-axis. So we know we want to set it to plat carries. So you should be thinking these two things, the projection and the transform. So we want to create an axis that's plat carry. And then we get a bunch of flats and longs are like x's and y's. You just go use Matplotlib to plot it, and you can tell it that it's in plat carry. So let's have a look at the solution. We'll step through it. Go backwards. Okay, so here we go. And there's a little bit of mangling of the data to get it in the form that you want. So we create our figure that we want to do, and then here's the bit of magic, which is we create our normal Matplotlib axis, giving it the projection keyword to say, I want this to be in plat carry. So here, this is where Cartopy comes in. You create your instance of your plat carry, and you'll get back your geo axis. Here we are, your axis. So we want to see some coastlines. So you can use the method coastlines on it. And now what we know is that we've told you the route from London to New York, and it will wrap back around, and you've got your lats and your longs. So there are several ways to skin this. So we've decided to unpack things with zip. So essentially for each destination, we get the place, and then we take out, looking up the dictionary for this place, we get the long, and we get the lat. So we've created this tuple. So you have a list of tuples, lats and longs, and we're using leveraging the unpacking and zip to get the list of all the longs and all the lats. You could have quite have easily just cut and paste and put them in if you wanted to. Okay, so now we've got longs, we've got lats, we've set up our axis, which we've created. Let's add our stock image, which is at low resolution. We've added a title, and this is where we're just creating a line now. We've done all the hard work. So we've got our longs, we've got our lats, we're using plot on our geo axis. So because it's on our geo axis, it understands about lats and longs. It's going to plot your line in the right place. We're adding some styling, which is just vanilla Matplotlib. We'll make it orange line width. And here we're saying it's geodetic. So this is going back to what Phil was saying. If it was in plat carry and you watch straight lines, then you put plat carry. But here we're saying it's geodetic. So the great circles. We're expecting to see, if you've got 2 points and you join the line, it's on plat carry, we're expecting to see some kind of curving there. So let's cut and paste this. So here we go with Mac. Yes, I copied something. Yes, I'm proud. So Command V. Done it. Well done. Thank you very much. Right. So, and it should be working hard. Let's run. Where's the lines? We're done. Run. Create the figure. And something's went wrong. Have I missed something? Over there. Yep. What have I done? Places up. Oh, idiot. Right. What have I done wrong? Not run the cell. That does help. Thank goodness for that. So I hadn't created the places, didn't know about the places. Let's rerun that again. Just getting too excited. Okay, so there we go. We've got something. This is what we wanted. But there's something a bit odd going on there, right? What's going on? Anybody? What's kind of obviously a bit weird with that? Juan's nodding and grinning at the back. Yeah, something weird's going on there. I remember I was going through this and I was like, Phil, what's going on? So basically, we've plotted our routes. We've got in plat carry. We've got some kind of curving going on there, which is what we're expecting. But you'll see, just as it went around the antimeridian, this went up here, this went along here, and this went back down there. What's going on? So this is something. This is Some things work, some things don't. So what we've actually done is there's a bit of cleverness in Cartopy, and it's basically saying in our route we started at London, went to Suez, went all the way around, which is fine. But if your start and end point are exactly the same, it'll think, aha, you're not plotting a line, you're plotting a polygon. And this is kind of what it's done. So thank you. That's for free. So that's clearly wrong. So we're going to fix that. So you could either just, at the moment, we've got we organized the sprint? Yeah, we have. So maybe that's something that we can fix. So if you were to ignore that part, that would be what we're kind of looking for. So yeah, so we had a heuristic in there that's not doing the right thing, and it's kind of a healthy thing when you actually become a user of your own software. You actually discover some things don't quite work the way you expected, but that's good. So we can fix that. That's fine. And there's other examples that we use much later on that do this in a better way, but we still have to fix that. So that's the example. Conscious of time, you guys need to go and get some snacks, have some comfort break, and then we'll crack on with the rest. Is that okay?
Yeah. So to add to that, let's take 10 minutes.
Yeah.
Hopefully that's enough. So there's tea and coffee and things and cold drinks out here, and I did a little recce a second ago because I can tell. I can just get the sense that you've got a sweet tooth as a group. You know, we like our candy. There is some snacks, but you have to go on a bit of a labyrinth mission to find them. As far as I can see, the only snacks that I could find are down the stairs, and then as you come down the stairs, you turn left, and then there's another left, and they're there. There's some goodies. So if you're after snacks.
There's also some food in the same room we have breakfast in.
Okay, there's food in breakfast room too. That's good knowledge. Thank you. Yeah.
Okay, so I think I'm going to start back. I know there's a few people missing, but we'll crack on. So we've actually we've got quite a lot of material to do. That's okay. We're just about to start. We've got quite a lot of material in there. We were actually fearful that we didn't have enough. We've got loads. So we're going to start pick and choose some things. So what we'll do is we'll rather than do some of the exercises in here, we're keen to get to some of the juicier bits later on. So what we're going to do is I'm going to go through them, talk through the solutions that are already there. If you've got questions, ask, try and answer them, and then we'll sort of catch up with ourselves. Yeah, sounds like a plan. So previously, before the break, we discovered that the world was indeed flat, and it went round the back. No, I'm only joking. So this was our estimate of Fogg's route that went round, but we've done a bit of digging. And we found that if you've read the book, what you realise is that here's London, and Fogg went down to Suez, but he went down the Suez Canal, took a boat, went across to Bombay, and then here from Calcutta to Hong Kong, he took another boat. So he went around this kind of peninsula here. So, and that's not quite representative of what's going on here. It's taken the greatest circle, shortest path between the points. So we didn't go down here, and it's not going round there. So it'd be nice if we could kind of look at that. So this is an interesting map. We sourced it from Wikipedia. So let's say the aim of this is really to use this image, which is a raster, georeference the image, so we can display our route over the top. But we've got a question. So given the work we've done this morning, a little bit of knowledge there about projections. What projection could this image be in, and why? Given you know a little bit about some of the metrics and some of the classifications. So there's a bit of guesswork, and maybe you've seen a projection that was on the sheet that this looks familiar, similar to. What are you thinking?
Well, it seems to be kind of bowed out on the side.
Yes.
So there was one of the projections that you showed us that was.
Yeah.
Okay.
Exactly. Who else? Yep. Robinson. Right. Okay. That sounds close. Yeah, because there's a bit that kind of curvature. Yeah. 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 So okay. So there's a bit of guesswork there. You can almost you've honed into that quite quickly. And we've done a bit of digging. Filled in a bit of digging, and it turns out that it is actually a Robinson projection. But you'll notice that it's slightly weird. It's got this bowing, but things are a little bit compressed at the top, and it's a bit odd because there's a bit of a continent missing here, Antarctica. Who goes there anyway? But so it's not quite right. There's something a bit strange going on. But there was a bit of compression there, and it was centered on the meridian of 11 degrees and 15 minutes. So we were going to give you an exercise, but we'll walk through it just and ask questions. So the exercise, given that image kind of looks like a Robinson, is to go to the documentation, which you know and love now. There's the list of projections. We're focusing on Robinson, so the task was to draw a Robinson with the map of the coastlines, which we know how to do, because that would be a method just on our geo-axis. But centre it on this meridian, 11.25 degrees, and plot that. So, knowing what we know, there's not a lot involved. So we create a figure, as before, and we know we were interested in Robinsons. So the projection, the target, what we want to see for the plot axis is the Robinson, and how we control where the meridian goes. There's a keyword argument when you look at the documentation that allows you to set that. So it's quite intuitive. So we know that now. We're adding our stock image, our decimated low resolution. You've got your splash of colour in there. We're adding some grid lines. We've seen this before. Remember, this is a geo-axis, so it's got this extra geospatial loveliness, so you can just add in your grid lines, and then you set your title. I've added a little title there, and that just works. So let's see what that looks like. Command, yeah. There we go. So it's kind of similar. We've got this bowing effect going around. I think we're onto a winner here. So we've done that, but you know, unfortunately, that map that we were looking at is not quite the same as I said before. There's a continent missing, and we know that however this has been drawn, this line's been slightly extended longer, and this one's slightly shorter. We'll see that when we plot it. So it's kind of close, but it's a little bit fruity. So plotted it, showed it. Okay, so there's something weird going on. And you can get that with some projections. It's went slightly off piece, and it's done some customization. So there's a fun exercise. It's a shame we kind of need to sort of rush past it, where we want to take that image and want to try and geolocate it to work out what the extents are. And we've got a little script that allows you to overplot. We'll run it, which will take the image. We've got a Robinson. We're going to try and correct it and line it up to work out what the extents are. Guess what the extents are, and then we're going to use that to make the plot. So see if I can do this right. So here we are. So I'm going to run this image geolocator. Oh, that one. There we go. So here we are. So we have got our map that we got from Wikipedia that's got the correct route that goes down and round, and under it we've got our Robinson. So what we can do is we can drag and drop. This is where you get to laugh at me, where I'm really rubbish at this. Oh my gosh, what's done now? Where's it gone? Yeah. Can you do it with the Mac mouse? It'll be quite easier.
Yeah. That's
defeated by the Mac again. In my head and shame.
Let's start there. It might be the screen mode potentially. Because that seems to work now, doesn't it?
Yeah.
There you are.
There we go. That would just go wrong again. So we kind of this could take me forever. So the trick is we're trying to bit of fappery to line these up. So Greenland's coming down, it's kind of close, just a tad to the right. Oh my goodness.
This is gripping, isn't it?
It is. I'm having fun, I don't know about you guys. Anyway, so that was the exercise, you were kind of doing that, and as it's running along, it's printing out the extents. So you do that, so it's kind of close enough. We're just playing around here to get four fingers. I'm going for it. There we go. Right. So, so when we do that, we got the extents. So that was the magic that we needed to take that image and then get the extents right. So we worked out the extents using that the program, the little example there, and the coordinate systems of these extents. So what do you think the coordinate system of these extents would be in? Yeah. Can I go that way? I'm getting good at this. Right, okay. You see those numbers? So they're kind of not that longs, are they? They're kind of weird numbers, aren't they? So it's suggesting that they don't look like that ones to me. What do you think? So what kind of projection are we in? Robinson, exactly. So we were in Robinson. These extents are in Robinson. So we just need to appreciate the data that we're using, and when we want to pass in the extents, that means we're setting the extent on the Robinson projection. So let's go back. So we've worked out our extents. We think they're in Robinson. And looking at the code, when we add, it was an image add that we were using. So let's look at the code we use. So we worked out the extents. We're doing our geolocation. We create a figure. We know it's all about Robinson. We're thinking of Robinson as the target projection that is. So we have created an instance of the Robinson projection. Remember, there was a shift in the central meridian by 11 degrees and 15 minutes. So we've got our target projection that we want to show our map in. So we create our axis. We get back our geo axis. This geo axis will be in a Robinson projection. We've set that up nicely. We've added some grid lines. We can add our coastlines again because it's a geo axis, and this is the magic. So this file that we saw, you can use image read. So Phil was talking about that. So we can use plot image read, which we load. We get the image. We load the image, so it's just a bunch of numbers, right? And then we're saying, well, actually, we want to take this image and we want to plot it onto our target projection, which is Robinson, which has been shifted. So you use imshow on our geo axis, which we've set all up. We take our data, we add it, that's the raster. Our extents, that's the extents which is calculated by fudging around, trying to get things to line up. This is our transformation. So our transformation, the numbers we're getting out were Robinson. We didn't think they were latching along, they are Robinson. And this is Matplotlib, just seeing the origins up on the top. We said it was global. Okay, so let's have a look at that, see what the outcome would be. Okay, so that looks kind of similar. So if I scroll up a little bit, see what the original looked like. There it is. We think we've geolocated, done with best endeavours. And you see there's a bit of weirdness going on here. This line, as I said before, it's went past outside the boundary. So that's like someone's hand drawn that, or they've done something a bit strange. In this one, it's almost like it's not quite right, but that's life, that's the way it is. But it's done the right thing. Okay, any questions on that? I'm really kind of happy that I kind of zipped through that, but the fact that you can take an image, you can know the target projection you want it to be in, you can geolocate it, work out the extents will be in that target projection, and then you're just using the things that we're building up in layers using Matplotlib using your friends that you know about, image read to read in the image, and image show on your geo axis with your extents. And you make sure that you have these magic words transform and projection, that you set them right. This is your data, and that's the target. Yeah? Is that okay? Happy to move on? Yeah. Oh, sorry, yeah.
I think I missed it. Going from the XY in the pop-up map, we manually
Yeah.
into the extent in the cell in the notebook. How did you convert the XY extent map into the extent list in the notebook?
So you're talking about these numbers here? These are the numbers when I was squishing the image.
Yeah, okay, so how do you get that from the squishing?
So yeah, so that was if so this program that we'd written, image geolocator, that was working it out for you as you moved it, because it was in the Robinson projection, and it was as you moved the image, it was recalculating the extents in Robinson's as it was going along. So as you moved it, these numbers were coming out, and once it all lined up, that was the extent of the image in Robinson. Is that, yeah? And it was just cutting and pasting those extents into the notebook. Yeah? Yes. Say it again, sir. So is that like drawing, right? Okay, so the question is filling in regions in different colours. Yes, yes, you can, and we've got examples of that later on. So and it's the same as Matplotlib. You can just change the face colour of a polygon, as you can change the properties of a line or a point. It's the same kind of things, the same controls. There's examples of that later on. Is that okay? Yeah. Okay. So that was fun for me. So I got to play with that, but I wasn't particularly. Is there any further questions on that? So quite happy with that to move on. Yeah. Yeah. So the question is about the extents, what they actually are. So that was just the bounding box of that image, and it was the X min, X max, Y min, Y max in that order, and the units were in the units of that projection, which Robinson's meters, I don't know, who knows? We could find that out. That's what they were. Any other questions? Yep. Okay. So that is that section. Is there an introduction? Let me get right. So we've been here, been there. So swap over to Phil now.
Okay, so we've now seen the what's going on here? Make that a bit smaller. We've now seen the how projections work and what projections are. We've seen how you add some data with Cartopy to your plot, to your axes, and we want to now talk about kind of treatment of those classes of data that we're adding, and kind of look at interoperability between those data types effectively. So I guess maybe I'll iterate what some of these, what the purpose of this section is, mostly to try and get some clarity on the types of data that we are dealing with, and once we know what kind of data we have, we know what, hopefully can know what kind of tools that are at our disposal. And also knowing what kind of data you have kind of gives you knowledge about what types of methods on the geo-axes you can make use of. So I don't want to take too long over this, but maybe we could do this interactively, in fact. So what I'd really like to start thinking about is the two classes of data that we've already been looking at. So vector data and raster data. So rather than working in small groups, let's work in one big group. What examples of vector and raster data have we already seen? And perhaps also maybe you want to kind of give examples that we haven't already seen yet. Yeah. What kind of vector and raster data have we seen so far? Okay, you said 2 words. You said lines and points. I'm going to take both of those words because I think they're both valid. And what class? Right, so this is kind of well and truly vector data in the geospatial terms for vector. Right? Yeah. The coastlines? Yep. So what kind of data are we looking at there? Right, yeah. Polygons. Yeah, it's vector data. Right.
The image that from the Wikipedia, and you have the images of continents.
Yep. Yeah, we had that stock image and we had the Wikipedia image, and that's an example. Raster data. Yep. Have you seen anything else? I'm trying to think myself. Any other kind of examples of raster and or vector data? No? States, yeah, it's kind of like the coastlines, yeah, vector data. Any other sources of raster data that you can think of? Yep, yeah, that natural Earth image was definitely. So thinking about stuff that we've not already seen, is there any kind of sources of these kinds of data? Yeah. Sorry? Television. Right, okay. Yeah, okay, it's big. Right, yeah. I've never put it on a Cartopy GeoAxis, but you could. It's an example of raster data, right? So I had a hand there, and then I'll... Right, weather maps, okay. So that's interesting. So weather maps themselves are typically what? Right, maybe. You could get like an SVG, which stands for scalar vector graphics, which literally is vector data, I guess. Maybe. Yeah, that's a good example though. So a weather map is going to be raster, typically. You're right. Cool. Yep. Okay, so continuous type model type things. So where might you get that kind of data from? How might it be stored? So do you get it as an image, or do you get it as some other format? Right, TIFFs, right. Cool. Okay, so there's clearly a separation here between kind of our vector and our raster data, and we kind of have already seen that you can add vector data with that add geometries and the pyplot.plot function, and you can add images with imshow. You can actually do stuff like p-color mesh in Matplotlib. There's a bunch of tools for working with these types of data. But sometimes you want to interoperate, and sometimes you want to convert from one to the other. And even sometimes you want to convert within that class. So you might want to say, if you've got 2 points, draw a line between the two things. So these are 2 subtypes of vector data. And that's what the purpose of this, I guess the main remaining section of this tutorial is about, is that interoperability. So yeah, as I say, that's what this is about. We're going to now look at Cartopy plus, and this is where we're going to change our focus a little bit and start looking at some of the kind of the wider ecosystem and bring in some of the tools that are at our disposal. So we're going to start by figuring out how we can do raster to raster conversions in various ways, vector to vector. We're going to look at some interesting application turning rasters into vectors. We could obviously be complete and do the final bullet point, but we just don't have the time for this tutorial, so we just ruled it out of scope. So with that, I'm going to hand over to Bill to talk about raster. Is that right?
Yep.
Yeah.
Okay, thanks, Phil. So, okay, so we've got to understand what raster is. So we're just going to tenuously pull on this Phileas Fogg theme again, going around the world. So we've done a bit of work, and we found some data from our Met Office Hadley Centre, the climate research. There's a link there, I think. Yeah, there is. There we go. Climate Research Unit. Okay, so we managed to find some data that was representative of the decadal mean surface temperatures during that period when Fogg was doing his journey. Just a bit of fun. So we've got some data, and we managed to we had to do a little bit of work to do that using IRIS, and there's a notebook there of how we can brought the climatology and anomalies together using IRIS. We're not going to explore that just now. You can do that in your own time if you want to have a look at that. But what I thought to do is we have a quick peek inside the data, see what's there, understand what it is, and then generate some plots. And it should come as no surprise, as Phil said, is that we are kind of we're standing shoulders of giants with Matplotlib, so matplot things just kind of work with a little bit of Cartopy added to it for the geospatial understanding. So we've got our file, which we are now going to use. So we're going to use NC dump, just have a peek inside the file, just to see what's there. You guys familiar with NetCDF? Nods? No? Shaking? No. Okay, it's just a, yeah, yay, someone knows. So what we've got, it describes things in terms of dimensions and variables. So it's just saying I've got some dimensions here, and that's their extent. I've got some time, some latitudes, longitudes, and some bounds. Okay, some variables. Okay, we've got mean surface temperature. It's three-dimensional, and these are the dimensions here. And there's some metadata there as well. It's describing some field values. I've got a long name, which is a description of mean surface temperature. It's got some units, some SI units, so it's in Kelvin. That makes sense because it's mean surface temperature. And there's some extra cell methods about some processing's happened on the data, and that makes sense because we know it's decadal monthly means. And it's also given some connective tissue to say, I've got this data, that's my payload, but there's other information that describes that. It describes the dimensionality, and it's saying decade and month number, and also time. So this describes the time. It's since an epoch. The calendar, it's got a calendar, and there's some bounds. So the time, you've got a point and a bound. So you've got bounded time. And here's a variable in here that describes for the latitude dimension of the latitudes. It's in degrees north units, okay, but information there. Same with longitude. So there's a bunch of information in there that we can pull out. It's got surface temperatures, and there's a little bit of extra information that NetCDF keeps, global attributes. It's like a dictionary, just of comments, history, things that have happened, sourcing the data, things that have happened to it. So there's various ways that we can read this in. We did explore a bunch of other things using NetCDF Python back to basics, used Xarray, but we decided there's too much. There's too much. So there is in the appendix, there's a notebook there where we explored and done the same exercise here, but we decided we're going to use IRIS, because IRIS is sort of goes hand in hand with Cartopy, and it allows you to sort of load your data, analyze it, and it uses Cartopy itself to do its visualizations. So let's pull in that theme, and we'll use IRIS and Cartopy together. IRIS, in a nutshell, you could just say it deals with multi-dimensional data. So just think of a NumPy array, and wrapped around that is the metadata that you care about. So data is just data, but what gives it meaning is the metadata. So times, latitude, longitude, information like that that describes where it is, and that's information that we need if we want to do a plot. Okay, so we have surface temperatures, we have units, information like this. So IRIS can read NetCDF files, GRIB, various other formats, and we can ingest it, examine it, and then we're going to plot it. So that said, we're going to import IRIS, and then we're just going to load our file, which we just had a peek inside. It's a bit noisy, and there are 3 months in there, because if we looked at time. Time was 3. And we process it to cover the 3 months, October, November, and December, to cover the duration of Fogg's journey, but it's decadal mean for the 1870s. So read this in and we get back a cube. So it's an iris cube, so think again like this NumPy array with metadata wrapped around it. You can do various things. So let's have a peek inside the cube, and it's saying, okay, this kind of maps on to what we saw inside the netcdf file. It's saying there's 3 dimensions, and it's kind of pulled together some of the metadata to make it a bit more readable. Mean surface temperatures, the units are in Kelvin, that's the extents, and it's saying I've got some coordinates that describe those dimensions. We've got time, we've got latitude and longitude, so there are coordinates that describe those dimensions, and there's some auxiliary coordinates. One on time that's saying, I know what the decade is, and one on time saying, I know what the month number was. Okay, and then there's these extra anonymous sort of attributes that it collects and say, well, I know about them, and here are the values. Okay, so let's just make sure, knowing what we know, that, yep, that's right. So we've got 3 decades, and they're all come in the 1870s. That's what I expected. And we're hoping that these are the 3 months of October, November, December. They're numbers, so if that makes sense, that's good. And time, you can have a look. It's got points and bounds. It's a bit noisy here. So you've got 3 points, 1875. You can actually ignore them because the way it's been actually meaned and aggregated. But what we're interested in is one of the bounds here. That's the first one. That's the beginning and the end of this bounded point. And it's from October, this is November, and that's December. And also, because it's a time coordinate, it knows what calendar it's in. That's useful. So we've got a bunch of information there, that's great. So we want to see it. Okay, so let's cherry pick out, let's focus on just October and say, okay, so this data is going to be raster data. So let's do some imports first. So we know about Cartopy. Got our coordinate reference systems. We're going to leverage some benefits of iris because we've read in a cube, and we give some convenience functions that are just wrappers around Matplotlib that do Matplotlib things, which we'll see, and we import Matplotlib itself. Okay, so what we're going to do here, we're going to create a figure, and here we're going to say, well, given my cube, just give me back the 10th month. We could easily have done this, saying, well, give me back the, you could easily, if you wanted to do October, don't go off paste, right? Equals cube, will it blow up? No, use something like that. Okay, it's all the same. So once we've now got our October cube, we've got the month, the decadal mean surface temperatures for October. So we're happy with that, but we want to see it. So here we're focusing on going raster data to raster data. So how's this going to work? We know we're going to have a couple of subplots, but what we're going to do is we're going to show a p-color mesh of that data, and we're going to show a contour ref. So these are just Matplotlib things. There's nothing different going on here. But what is different is that we've added this projection word again. We keep on seeing this again and again, but this is just saying, okay, this is standard Matplotlib, but the projection is in Robinson. I get back a geo-axis, and here we're using iris to say, because iris speaks in cubes, okay, and it'll say, well, here's my data, I'll give you my cube, can you do a p-color mesh? And essentially it's going to call Cartopy and Matplotlib to do that, but it does a little bit of work for you because it understands all the metadata, the lats, the longs, the time, all that kind of stuff. That's fine, nothing new there. We get the title, we add our coastlines because this is a geo-axis, it's in Robinson, and we're setting it global, so we've got full extent. So that should be a p-color mesh, our first subplot. Let's do the same again, same deal. Create another subplot, projection is Robinson, we're doing a contour ref, we're using iris because it's easy in one line. We pass in our cube of the data that we care about, and we add our coastlines, do a type layout, and we run it. So, and there we go. So we've got some data, it's Robinson's, it's got that, it's as we expect. It's kind of looking similar to that Wikipedia raster that we had, but here we've got our block plot of our data, and here we've got our contour ref plot of our data. So that's kind of useful, that's kind of handy. But, you know, we've said several times that you can take data and reproject it into a different projection from its native projection, and you can do that. That's quite easy. But we know that, going back to the example we had with the wiki image, that it was in Robinson. Okay, so let's change that. So here we calculated our extents. We create a figure, and with that wiki image, remember it was off. The meridian was offset. Our target projection is Robinson. We're adding some, so we've got back our geo-axis. We're going to add our grid lines because we can do that. Quite a geo-axis, quite our coastlines. Now we've set that projection up. It's in the format that we had for the wiki because we've got our extents and things. We're going to read our image that we had before, and we're using, which is just a Matplotlib image read. So we've got our data. That's our raster data. And now we're just going to say we've got our geo-axis, and we're going to plot that with our extents that we've done before. We've seen this before. This is not new. We've got a transform word saying this data is in Robinson. We add a global. And okay. If I run this, it might be actually helpful to see what we see. Oh, wait. Yeah. Yeah. So has this been copied twice? Yeah. Is it dot? Is it? That's right. Previous one, yeah. Great. Someone beat me to it. Okay, so we've now created our plot as before. We knew the extents. We've used our Robinsons, and we've got the wiki image as we wanted before. So using Cartopy, we can reproject this raster image, as I said, to a non-native target projection. So our data was all in Robinsons, but we can easily say, well, actually, let's see that image, but we can put it in Platcarry. And the way to do that is say, you set the projection to be what you want it to be, which is Platcarry. Our data, which we'd loaded previously in the previous cell, that's in Robinsons, that still stands. And Cartopy will reproject it into your target projection, which should be Platcarry. And there we go. Okay, so there's a little bit of work there because it was working hard to, because it's reprojecting that whole image. So there are a lot of things that can do that. Raster, you guys heard of raster.io? No, it's kind of built on GDAL, so it's got all the smarts of GDAL in there. It can do that kind of thing. But Cartopy is a good option to use. Do we want to run through these kind of exercises? I don't see great value in talking about those, but it's just taking the image and you're just doing the same thing. You know that it works for images, for rasters. All the exercises were just overplotting the temperature data on top of it. So this should come as no surprise that you can do a contour. So on this image here, it'd be quite easy to then change your projection if you want to. And the temperature, decadal surface temperature that we had, we can just do a contour F, or we can do a p-color mesh on top of it, so you can mix and match. So that's the power of being able to reproject, create the projections that you want using raster data. Was that too fast? Is that okay? Or is it worthwhile going through some of these examples? What do you think? Yeah, okay. So we know about how we do our plotting with our image. So what was the exercise? The exercise, Iris is doing a lot of the heavy lifting for you, okay, because we load the data as a cube. So what you plot the decadal mean surface temperatures for October, which we've done before. Use either a block plot or a contour plot over a wiki image in a Platkai projection. So here we go. So what we're interested in, what's the target projection? It's Platkai. So we're thinking, let's create an axis. We're interested in Platkai, and we set the projection keywords. So we've got the right geo-axis back. We're adding some grid lines. We've seen this before, and we can add some coastlines. This is reading our raster image, which is the wiki image. We read it in. We've seen this before. You then use on your geo-axis the image show. We've worked out our extents, which was in Robinson. We set to be global, so we've got a full image. And this was all the difference, really, this exercise was looking for you to use, was to, once you'd set all this up, which we'd seen previously, was to overplot the temperature data for that decade of 1870, and using Iris to do that. So it's bringing together those two examples. So we've got our cube data, we do our p-color mesh, and we plot it. So let's have a little look at that. And here. Okay, so I had to do a little bit of work there. So here we go. So we've got, as we expected, we wanted to be in a Platkai projection. It's done that. And we've got our, which was Robinson data, it's reprojected it into Platkai, and we've used Iris because with its data to do a p-color mesh of the temperature data. Is that what you were expecting? Were you kind of starting to join these little bits of the jigsaw together in terms of what you want, getting your data, being able to get a geo-axis, set your projection to be the target projection that you're interested in, understanding what projection your source data is in, and then setting these up correctly. Any questions? Is that too fast? Okay. Should we look at the extension? I don't think it's really worthwhile. But the main point here is that you've done plots before, you've done contour F, and with Cartopy it's just allowing you to do the same thing with a little bit of minimum effort. And we did lean on Iris to get the data, but there's nothing really radically different there. And under the hood it's using Matplotlib and Cartopy itself. Okay. Now we're doing for time. So given that we are okay, so we're talking about this interoperability. So we've talked about getting an appreciation of going from raster to raster. The next section don't need that, let's do some tidying up. So we're happy with going from raster to raster. So we're going to dip in a little bit to vector, and we kind of appreciate now what vectors are. We're talking about points, we're talking about lines, we're talking about geometries. What might be involved in those kind of operations? What can we do? What can Cartopy offer that makes our life easier? So let's first talk about points. Let's start there and move forward until we get to geometries and lines. So if we want to take the Cartopy has a coordinate reference system, and on there are some methods that help us, that does the hard work, and it uses Proj4 to do these transformations. So it's easy for us to, these methods, transform point and transform points. So let's see how easy it is to transform one point from one coordinate system to another. So we're going to, again, import the coordinate reference system from Cartopy. And as an example, something slightly different, OSGB, everybody heard of OSGB? It's like the Ordnance Survey for Great Britain. It's like a projections just around Britain. Because we can, right? And that's one that's used generally for some of our weather. And we've got geodetic, so that was the spherical coordinate system. So we'll go from one to other. So convert from Ordnance Survey GB, which I think is in meters, it's a bit weird, to lat long. So we've got a point, which are in eastings and northings. We have our geoid. So we're introducing this transform point. So maybe it's worthwhile jump into the Cartopy documentation. So we've got a whole bunch of methods that are on our coordinate reference system. And one of those is transform point, and the plural is transform points. So here you simply pass in your x and your y point and your source coordinate system of those points. So that's almost akin to when you were doing a contour F, you passed in your lats and your longs and used the transform word. That was a way to sort of say that's what the coordinate system of the source data is in. So that's the same with transform points. Let's see if I can jump back. So we have transform point, our x and our y point. Here they are, eastings and northings, and it's saying actually these are OSGB. What's OSGB? That's our OSGB projection. So it's saying transform these x and y points in OSGB, and the method has been called on geoid. So that is the target that you're going to go to. So this is projection, the domain from and the domain to. You can run that. So I guess that's right. That's the lats and longs of that point, going from OSGB to geodetic. And that kind of extends. You can do that for multiple points. So that's a point. The next thing up from there is lines. So that's connecting 2 points to make a line. So it's subtly different. You can project a geometry, but you use the word project instead of transform, because what's actually happening under the hood is that if you imagine having 2 points and a line, and if there's a boundary, you see that the line was going to cross the antimeridian. Cartopy has it's not precise, but it uses a numerical tolerance to work out where that cut might happen. Remember the orange that we kind of flattened out? So if you had a line that was going to cross in the northern hemisphere, Cartopy works out where the breaks are. And it's not precise, so if it was precise transformation, we'd use the transform word, but there's a bit of cleverness going on, and that's why we've hinted at that by using the project keyword. Let's have a concrete example. So we're going to lean on, like I said, Cartopy uses Geos and it uses Shapely. So we're going to import Shapely geometry, and then what we're going to do is we've got New York to Honolulu, difficult to say, and we're going to create from there a line string. So we've got our longs and lats, we put them in, and we'll create a Shapely line, which is a line string. And we have got a plat carry projection, and okay, we want to convert this from plat carry for this line to plat carry. So there it is. Not, yeah, it's that exciting. Thanks, Juan. So yeah, it wasn't too exciting. So let's put it in some context. Yeah. Just this line here. It's so the question is, what is that thing? So that's just a Shapely line string. No. You got clearer definition of that? That might. I don't feel I answered Juan's question really.
Well, yeah, the line string is
Yeah, it's not a string. Yeah. Yeah. No. So it's like a shapely thing, like a primitive that understands that's a line. So we're going to use that, and Cartopy understands that. So here, yeah, let's put that into context. So, okay, you've seen a pattern here. It's almost like a factory of a way that we bolt these things together. We create our figure. We create our axis. We're interested in plat carry. We get back our geo-axis. And what we can do is we can add geometries to this by using the add geometries method on the geo-axis. Here's our line. It's in plat carry, and these are just standard Matplotlib keyword arguments that are going to describe that. We're adding edge color, face color. So this probably goes back to your question, the gentleman at the back, about if you have a geometry, you want to change the color. This is kind of the way you would do it. Let's add some coastlines and let's do a plot. Slightly more exciting. Okay, so it done as we expected. New York to Honolulu. And that was not just a line, but our geometry line. So, so if we want to represent that line as a great circle, okay, so you might start thinking, what could we actually do rather than a straight line? We're going to take our line and say it's, remember at the beginning we created a geodetic projection? So we're saying this line is a geodetic line, but project it to a plat carry line and plot it in a target projection that is plat carry. We're using add geometries to add that line again. Let's see what that looks like. So as before it was a straight line, but now we're saying it's actually our great circle, which we know is going to be a curved line on a flat plat carry. So it's kind of behaving as we might expect, and we've sort of seen that behaviour before. So there is an exercise. How do you want to just walk through it? Let's do it. Yeah. Okay. So I've done a lot of talking, and you've done a lot of kind of sitting and listening, which we don't want that to, because it's a tutorial. So let's kind of try and consolidate some of that all together. We'll give you some time to do this exercise. We'll be walking around so we can help you. So what we've got to do, we're going to construct a line string. So this line string is a shapely object between Yokohama and San Francisco. And we've got the lats and longs there. Project this line using our project geometry, using both plat carry and geodetic as the source coordinate systems. Plot the lines using Cartopy and observe how they differ. So how, you probably guess what they might look like, but let's find out what they do. And if you've got time, when you nail that, you understand it and you're happy with it, the extension is to devise a way of constructing the line string such that it crosses the antimeridian when using the project geometry. So there's a little bit of thinking about there, it's a bit sneaky. So have a think and try and tackle the exercise.
I just wanted to add, if it's not clear, the wording's pretty terrible. We're asking you to call that project geometry in multiple times. Basically, project it for your first line string and then project it again for geodetic, and we'll get two results. And what we want to know is, in what way are those results different? I guess that's the point of this exercise. Okay.
Great. Yeah. Okay, so I'm going to crack on. Let's have a peek at what we've got and see if it's kind of close to what you had. So we know that we're going from Yokohama to San Francisco, provided with those lats and longs. So we create our shapely line string, plug in those coordinates. We've got creating a plat carry projection, and then we're going to create our two projected lines. So we're projecting the geometry. So we've created our geometry, which is our line. And we're saying, okay, this guy here, this line here, is actually a plat carry line. And this one here, actually this is a geodetic line. And we're using the project geometry for this line using this projection. and we're projecting from Platte-Carry to Platte-Carry, geodetic to Platte-Carry, and we create these two projected lines. Okay, so now we've done the hard work. Hopefully that was, you got close to sort of seeing that was the part of the exercise. And now we're going to again do the same thing. We're going to create a figure, and we're going to have our target projection for this axis to be Platte-Carry. And then we're going to add our lines to that axis. Remember, this is our geo axis. If we want to add geometries, there's the add geometries method that you use on it. Okay, it's you need to pass in an iterable rather than a single thing, so that's why we pass in a list. So you've got your Platte-Carry line, you've got your geodetic lines. So we pass in our Platte-Carry line, and we're saying, okay, this is a Platte-Carry line, that's the Platte-Carry projection. We're going to add some colour to it so we can discriminate between the two. We've got a blue line for Platte-Carry, face colour none, line width. And then we do the same for the geodetic line. Same deal, we've done the hard work up here, we've created our geodetic line. We say, okay, add it to the same geo-axis, and then we make that red, add some coastlines, and then let's see what that looks like. So here we are. So what's interesting here is that you've got San Francisco, Yokohama here. So Platte-Carry line is the blue line, and as you'll see, it understands straight lines, and this is joining as a straight line from between these 2 points. The red line is the geodetic line. Geodetic lines always we're thinking spherical, so we're thinking, if you join 2 points of a great circle, it always takes the shortest distance. The shortest distance between these 2 points is not the route that the Platte-Carry line is taken, it's actually gone round the back. But again, Cartopy is clever to know where the boundaries of the map is, the discontinuities are, the antimeridian, and it's clipped it properly and it's brought it back. So that is the shortest distance, that's the geodetic line. You might have thought that the geodetic line would have bent and gone across here. Did some people think that might happen? No? That would go around the back. Did anybody get that far? Some nods? That's good. Did we want to do the extension? It's just, no. Okay. Projection geometries, yeah.
Okay, so we've seen project geometry, and Bill showed us it projecting lines. The same method works for polygons, shapely polygons. So we're just going to construct, this is pure shapely, no Cartopy here. We'll just make a polygon and sine and cos of some number between 0 and 2 pi. You end up getting a circle. So cool. It's a circle in Shapely, and Shapely renders it for you, which is kind of neat. Okay, we're going to project that. Okay, so I'm going to say that these coordinates are spherical coordinates. The lines between those coordinates are great circles, and I'm going to project it to Platte-Carry. And okay, not that exciting. We get a circle projects to a circle when it's geodetic, right? However, if we change the projection of our target slightly, so instead of us having the central meridian at the middle of the map, we switch it around by 180 degrees. That circle that's centered at 0, 0 actually, because that's what our implementation does. If we project that to some different projection, we'll see a different result. Okay. And what's happening here is that polygon now covers, one half of the map and the other half of the map, and Cartopy's realized that and filled it in for us. Okay, so let's follow that same old pattern, add geometries, the projected geometry in the target coordinate system, and have a look. Okay, so there's that circle centered on 0, 0, and it's cut round. Okay. The one really important kind of subtlety, detail that you need to know about geometries on the sphere is that you need an extra piece of information to determine which bit you should fill in. Right? So on the sphere, just imagine you had a polygon that was defined that tracked all the way around the equator. Okay, which side of the hemisphere should an algorithm color in? Okay, and we need to figure out or have some convention to determine that. If you think about that in those terms. And Cartopy follows fairly standard convention of using counterclockwise winding order. And I guess we can demonstrate that quite nicely by simply reversing those coordinates on that circle that we were manufacturing. And I'm going to call it inverse circle, so hopefully this has given you a sense of where this is going. Okay, I'm going to use the same call that I did before to project the geometry to that projection that requires a cut. And we don't get two halves of circles. Okay, we end up getting the whole thing minus those two halves of circles. Okay, so I hope that makes sense as to what's going on. Polygons on the sphere, the winding order is really, really important, and when you project it, Cartopy is honoring that. Okay. There are some Shapley's great for dealing with this stuff. You can change the order really easily. You can check what order your polygon is in. So, yeah, these tools are out there and are super useful. Any questions on project geometry? Basically, what you're seeing here is what's happening when you're adding data to Matplotlib geoaxes. But what we're demonstrating is that this doesn't need Matplotlib in order to project those geometries. This is actually a really general purpose algorithm that can project geometries for you. Okay. So, we're running low on time, and I'm thinking there's a nice section here about distance and distance on the sphere, but I think we're just going to move over it. Basically, Cartopy has the functionality to do geodetic distances. There's material here for you to have a look at, and I think we've not got the time to go into that in too much detail, if I'm honest. I will touch on geometry predicates though, because that's kind of useful. So, one depends on the other, doesn't it? Of course it does. Where are we? I could just execute the cells and walk through it. Yeah. I don't want to kind of go crazy with output there, or make you dizzy or anything. But I'll follow your advice. Right. So basically, let's construct a line string with lots of lats and longs. Okay. This is just pulling it out there, and this is using the same pattern as just seen. Project that line, it's geodetic, and give me back a geometry which represents the geodetic line in plat carré between those points. That's basically all that's happening here. Okay. The other thing that I want to show you is that kind of interplay within Shapely, really, or GeoPandas if you're using GeoPandas or some other tool. And so what I've got hold of here is some natural earth land data. There's a shape file here containing the polygons of all the land on the globe. Okay. And there's some functionality in Cartopy that will do that for you. There's shape reader module. but GeoPandas would work just as well. Fiona would work just as well. PyShape, there's a bunch of different options here. The important thing is we end up with a list of shapely geometries. However we end up there, it doesn't really matter. Right. And let's fix them up a little bit. Okay, so that is a shapely representation of the kind of the geometry that is land. And what we can do is kind of do a shapely intersection to figure out, of that track, that great circle track that we just produced, pick out only the bits that cover land. Okay. And now our geometry starts to get a bit speckledy because this is, I think, North America and this is the Atlantic, perhaps. So we end up breaking up the path, the great circle path. And this is where kind of there's tendrils into the previous section because now we can compute the distance of that track. Don't go off piste is the moral of the story. Yeah. Yeah, let's move on from that. So I guess what this was hoping to get at was that there's a really nice interplay between Shapely and Cartopy here. Cartopy will give you an awful lot of functionality in terms of spherical work. It will give you distances. Shapely will give you really powerful predicates, including intersection, to kind of join, mash together vector data sets in a really intuitive and powerful way. And they come together and form some really nice behavior. So I encourage you to take a look at this exercise offline. It will kind of hopefully be self-explanatory. Yeah, but we're running low on time. We're running low on time to show you anything about Folium and SciPy leaflet. So maybe this should just be a little run it and see what happens type activity. I won't even talk about the code. If you have any questions about Folium, Philippe, could you put your hand up, please? The person that's looking the other way. So it's some really cool functionality, web-based, in the browser type visualization. Check it out. There's also similar tools like IPython leaflet and GeoViews, both awesome tools as well for visualizing this interactively in the notebook. You might like to check those out. That is all we have time for vector to vector. Okay. There are 2 more sections. And less than 10 minutes. Yeah. Yeah. So one of the things that we're going to do with this tutorial is bring in a guest speaker, Juan in the corner, and I think we should bring him down in a second, or even now maybe. Come on down. So Juan Núñez Iglesias. Hopefully these notebooks are useful to you, and if you're into this space, take a read over them. We're here all week. We'll be here for sprints and stuff, so check them out. But basically, that Wikipedia image that we've got there, it'd be really great for us to pick out that track, okay? And we asked Juan, who's Scikit image fame, good guy, to do this for us, and he did. He hacked it out last night. And yeah, I don't know if you just want to talk us through.
I'm happy to go through it.
Yeah.
Yeah.
Come in.
All right. So hopefully I'll remember what it is that I did. Okay. And this is weird inverted scrolling. Okay. So the first thing that you need to know, which we haven't, this is not my code. Oh, okay. All right. Can I? Okay. And you have a weird European keyboard too. Okay, so I can skip all this. That's interesting. What is all this? Like, you've thrown me in ahead of time. I'm fine. All right. Okay. So Phil did something here that I don't understand. CCRS is not defined. Did I not? Oh, you haven't run all this. Okay. Right. Great. Okay. We're in business. Awesome. All right, so here's what happens. So if we look at the image that we got from Wikipedia, which is here, it looks like there's actually 5 colors: white, gray, black, yellow, and blue. But if you zoom way in on these pixels, there's a bit of anti-aliasing going on. So you've actually got some blue and then some light blue on the edge. And here you've got some light gray on the edges and so on. So we can't just go and look for blue, black, and yellow pixels to get the track, which is what we would want to do. But there's a cool SciPy function called vector quantization. And what that does is, where am I? Here. So this is scipy.cluster.vq. If you give it an array of colors, and then you quantize, you give it an array of pixels, which are sort of 3 values. So it's an array of number of pixels by 3 values. The vector quantization function will tell you which of those colors is closest to each of those values. And then we can transform back and just say, all right, make that pixel that color. And then we end up with an image of only 5 pixel colors, which are white, gray, black, and yellow. So that's what all this code is doing, and I don't have time to go through in more detail than what I just did. But let's just see that it worked. So you can see that we've got the 2 images and they look the same, but thanks to this fancy Matplotlib notebook mode, if I can scroll, zoom to rectangle, if I zoom in here, let's zoom in even a bit more. So do you see that here, this pixel here, this is the original image, is some weird intermediate gray, whereas over here it's gone back to the background gray, and so on. So you've also got some light blue colors here, they're gone. So now that's good because we can say, all right, to get the track, I'm just going to get the black pixels, the blue pixels, and the yellow pixels. And the other thing is you've got the names of the cities, and we're going to get rid of those in a second. Okay, so if you look back at my colors, let's see. All of the colors that I'm interested in, which are black, yellow, and blue, have zeros in their values. Whereas the colors that I'm not interested in, which are gray and white, they don't have zeros. So I'm just going to find all of the places in the images where some channel is equal to 0. Then I am going to use ndimage.label to find the connected sets of pixels. And then we're just going to discard all of the pixels that are, all of the pixel groups that are not part of the largest pixel group. So if we do that, it would be nice to actually just show the track, so I'll just do it. Track fat. And the reason I call it fat, why did that not do something? Oh, figure, all right. So X. So I'm just going to do subplots. Okay, so this is our track. It looks perfect, except if you look at it, it's a little bit fat in places. So let's go here. You can see that it's thicker than 1 pixel, and we want to have like a track of single pixels. So scikit-image has a skeletonize function, and that's what we're going to do. So probably I would do this in 2 steps, but that's fine. So we take the track using skeletonize, and then what we're going to do, and I definitely don't have time to go through this in detail, is for every pixel, we're going to look at all the neighboring pixels, and then first of all, we find the leftmost pixel, and then from there, we look at the neighbors, find the point in the track, and then we add that to this list of, what do I call it, path, to this list of point coordinates. And that ends up giving us our point-to-point path around the world. Okay, and now we can plot it. So point-to-point, now we have latitudes and longitudes. And we can use, so that this is now longitudes and latitudes. We can use all of this Cartopy niceness to plot this as actual Matplotlib lines. And you can see that these are lines now and not pixels. So it's a nice, yeah, now it's vector data. And now Phil can take over.
So I guess there's more work we can do there, right? So this gap is very clearly there. It would be nice if it wasn't there. But it's an artifact of the actual image. That is a gap in what's represented in the underlying image. So I kind of hack away at that and basically compute the missing gap using a bunch of really powerful Shapely functionality, not really iris Cartopy functionality itself, and we end up with a root. And I guess really the point of this section is about showing you that we've got access as a community to a really diverse and powerful set of functionality. Scikit-image is a good example of that. But there are so many others as well. And we can kind of bolt these things together and build some really powerful tools. So the tool that we've built here is using some image processing to pick out the track from an image, which is kind of cool. We need to do a roundup, basically. So the final thing really that we wanted to get to is the roundup. Obviously, we have kind of needed to rush through this at the end, which is a bit of a shame. But hopefully, you've got a sense of the kind of broader scientific Python geospatial community, kind of what's there and what's available to you. Ironically, even though we've run out of time, we've not even touched the sides really in terms of what's available in Cartopy. Like, I'll make this a bit bigger. Cartopy does kind of web map service, yeah, tile ingestion. It's got some interesting kind of digital elevation model access in there. Yeah, even like wind vectors and transforming wind vectors is kind of an interesting thing. So a bunch of tools that Cartopy has that we've not even had a chance to talk about. If any of those are of interest to you, then as I say, Bill and I are here all week and I'm happy to talk at any time. There's a final exercise here, which obviously we don't have the time to do, which basically tries to recreate this image. You may enjoy having a go at that if you find the time, and I'd be happy to help out if you get stuck. But yeah, that really wraps up mostly what I wanted to say. There's a huge kind of collection of people and tools that have come together to form a really powerful ecosystem, and we can just exploit that, and it's fabulous. I love it. Cartopy just bolts some of those things together, gives you a bit more geospatial richness, project geometries, for instance, and imagery projection, stuff like that. A big thanks to Kelsey Jordahl, who's not here, but who gave a really great geospatial tutorial back in 2015. You might like to check that out. And Jules Verne, who wrote the excellent Around the World in 80 Days book, and it's free, out of copyright. So, you know, go and get it. It's a good read. It's good fun. And as Bill says, we will be sprinting this Saturday, Sunday on Cartopy, and Cartopy and Friends probably. There's a few bugs that we want to fix. There's a few features that we want to add. And if you're interested, then come and join us. It'll be a lot of fun. Yeah. Any more, Bill? Okay. Just like to say thank you to Juan for coming down and giving us a lightning tour of how he did his image processing. And thanks to Bill for helping out. Great. Have a great